Welcome to another deep dive. Today we're going to be looking at something pretty fascinating. It's where geometry and computer vision kind of collide. We're going to be talking about Flatland. Specifically, we're going to be diving into a paper called A Computer Vision Problem in Flatland.
Written by Agrawal, Connolly, Cronell, Duff, and Thomas.
Exactly. Now, you might be thinking Flatland like that old book.
Right.
You're absolutely right. But we're adding a computer vision twist this time. Just imagine cameras that actually exist in a two-dimensional world.
Yeah, it's a really cool thought experiment.
Yeah. And as you can imagine, it leads to some pretty wild geometric insights.
What's really cool is that the paper looks at a very specific problem. Imagine two sets of labeled points that exist in different planes.
Okay.
The big question is, when can those sets be projected onto the same line so that those images look identical? It's like asking when two Flatland cameras, each looking at different sets of points, could capture the exact same image.
So it's not just about whether or not these projections exist. It's also about understanding the specific conditions and constraints that make them possible.
Exactly.
And to get to the bottom of this, the authors had to go deep into projective geometry.
That's right.
And they start by formalizing the problem using this concept of projective space, denoted as PK. Now, for those who need a refresher, points in projective space are actually represented using homogeneous coordinates, which use an extra dimension to represent points at infinity.
Right. And in this Flatland scenario, we're dealing with P2, which is our two-dimensional plane.
Right.
And P1, which is a line. A Flatland camera is then defined as a linear projection from P2 to P1.
Okay.
What gets really interesting is that the problem basically hinges on understanding where we can place these cameras.
Okay.
Or more formally, the centers of these projections, so that they produce those identical images of two different sets of points.
Okay, so we're in Flatland, we've got our cameras, and now we're trying to figure out where to position them for these unique projections.
Exactly.
But before we even get there, the paper actually addresses a super fundamental question. Do these projections even exist in the first place?
Right. You have to know if your whole premise is even valid.
Exactly. And that's where Theorem 2 comes in. And I gotta say, it is a pretty mind-blowing result.
Theorem 2 states that two sets of labeled points in P2 can have the same image on a line, if and only if they are themselves projections of the same set of points in P3.
So that's where the connection to 3D reconstruction gets so clear.
Yeah.
So you're saying that two sets of points can only look the same in Flatland if they're basically shadows of the same 3D object.
It is. Imagine a 3D object casting a shadow on different planes in Flatland.
Right.
Theorem 2 tells us that if those shadows look identical from certain viewpoints, then they must have come from the same 3D object.
So we're not just playing with points on a plane.
Right.
We're actually getting glimpses of a higher dimensional reality.
Exactly.
And that link to 3D reconstruction, I mean, that's a massive area in computer vision, right?
Oh, absolutely. It's a fundamental problem. Think of it as trying to build a 3D model of something just from 2D pictures taken from different angles.
Okay.
This paper shows that even in a simplified Flatland setting,
Right.
those same core challenges and insights still apply.
And speaking of computer vision, the paper also brings up this concept of the fundamental matrix,
Oh, yeah.
denoted as F. It's basically a matrix that captures the geometric constraints between two pictures
Right.
of the same scene, but taken from different viewpoints.
Exactly.
It's like this bridge between the algebra of matrices and the geometry of the scene.
It really is. And theorems 4 and 5 in the paper really connect this fundamental matrix back to our Flatland problem. They essentially state that finding those special camera placements in Flatland is the same thing as finding a very specific fundamental matrix that relates those two sets of points.
So it's like we're seeing two sides of the same coin.
Mm.
One side is Flatland and the other is our 3D world, and they're linked by this fundamental matrix.
Exactly.
Wait, hold on. There's got to be a catch, right? Theorem 6 hints that even if those camera placements actually exist, actually reconstructing the 3D object in a way that perfectly matches all the viewpoints isn't always possible.
Exactly. It's like having pieces of a puzzle that seem to fit together in pairs, but then when you try to put them all together, some pieces just don't align.
Right.
There can be inconsistencies. The paper really delves into this, showing that even when you have camera placements that create identical pictures, reconstructing that 3D object may not actually be consistent with all those viewpoints.
So even in Flatland, the world of 3D reconstruction can be pretty tricky.
It is.
Okay, so we've tackled this big question. Do these special projections even exist? But now we're on to the next challenge. where do we actually put those flatland cameras to actually get those identical images?
Right. To answer that, the paper takes us on this really cool journey through invariant theory.
Okay, invariant theory. Break that down for us. That sounds intimidating.
It's a really elegant idea. Invariant theory is all about finding properties of geometric objects that don't change or remain invariant even when we change our perspective.
So it's like finding the core essence of a shape,
Yeah.
something that's true no matter how you look at it.
Exactly. And in our case, we're focusing on invariant properties of
Yeah.
points on a line,
Boy.
our P1 image line, under a special group of transformations called SL2. You can think of SL2 as transformations that preserve area, which is super important when we're talking about projections.
Okay, so we're dealing with these transformations, but how do we actually find these invariant properties?
Well, the paper brings up these bracket polynomials, which are this special type of polynomial that are constructed using determinants. These polynomials have this really cool property of being invariant under the actions of SL2. They're like our building blocks for invariant analysis.
So these bracket polynomials, they capture those unchanging properties that we're looking for.
That's right. And a key result that helps us understand these bracket polynomials is Kempe's theorem. This theorem basically gives us a way to generate all possible SL2 invariant polynomials using these brackets. It's like having a cookbook for invariant properties.
So now we can systematically explore the geometry of points on our image line without getting bogged down in specific coordinate choices.
Exactly.
But how do we connect this back to camera placement?
Well, that's where the camera centers variety comes in. Using these bracket polynomials, the authors define an algebraic variety that captures all the possible pairs of camera centers that could produce identical images of our point sets.
So it's like this map telling us exactly where those flatland cameras can be to achieve our goal.
Precisely. And the dimension of this variety tells us how much freedom we have in choosing those placements. As we add more points, the dimension of this variety changes.
That makes sense. More points, more constraints.
And Corollary 18 actually gives us a hard limit. It states that for 8 or more points, no solutions actually exist.
So there's a limit to how many points we can match up in this way.
Exactly. It highlights this really cool interplay between the number of points and the constraints on those camera positions.
Okay, so we've laid the groundwork: projective space, the fundamental matrix, invariant theory, and the camera center's variety. Now it's time to get specific.
Yeah, let's get into it.
The paper explores the cases of 4, 5, 6, and 7 points, each with its own geometric twists and turns.
Right.
Shall we start with NA 4 points?
Absolutely. This is where things start to get really interesting. You move from those general principles to really specific geometric construction.
Awesome. Let's dive in.
So with 4 points, Theorem 20 tells us something really cool. You can actually choose the first camera center completely freely.
Okay.
But then the position of the second camera gets a little bit more constrained. It has to lie on a conic section, a curve, like a circle, an ellipse, a parabola, or a hyperbola.
Okay.
So it's not just any point anymore. It's tied to a specific geometric shape.
So it's a pretty big jump in constraint.
Yeah.
We go from complete freedom to suddenly being restricted to a curve.
Exactly.
And you mentioned that this conic section is determined by something called a conic cross ratio. What exactly is a cross ratio?
A cross ratio is a way to measure the relative positions of 4 points on a line or a conic. It's a super fundamental concept in projective geometry.
Okay.
And it actually stays the same even if we project those points onto another line.
Okay.
In our case, the conic cross ratio of the second set of points, along with the position of the first camera, actually determines that conic that the second camera has to lie on.
So knowing the cross ratio and the position of one camera, we can actually construct this conic that restricts the placement of the other camera.
That's right. It's like the points themselves are dictating the rules of the game.
It's super interesting. And figure 4 in the paper gives us a visual guide to this whole construction.
It's a really elegant construction.
Yeah.
You choose that first camera center, and then you pick an image line. Then you project the first set of points onto that line and use the cross ratio to find a very special point. It's called the center of perspectivity.
Center of perspectivity. It sounds important.
It is. This center of perspectivity helps us determine the position of that second camera by making sure that the cross ratio is preserved in the projected image of that second set of points.
So there's like this hidden relationship between the points and the camera placements.
Exactly.
And this all comes back to our camera centers variety, right?
Absolutely. In the case of 4 points, denoted as C4, it turns out to be a hypersurface in a 4-dimensional space.
A hypersurface.
It's basically a surface embedded in a higher dimensional space.
Okay.
Theorem 26 goes into more detail about its properties, and one key takeaway is that we can reach any point in either of our 2D planes by choosing the right camera placement on this hypersurface.
So we have this higher dimensional object representing all our possible camera placements, and we're kind of slicing it up to find the specific placements that work for our 4 points. And those slices, those fibers of the projection turn out to be conics.
That's exactly right. It's like those conic sections keep popping up, reminding us of how fundamental they are to this whole geometric problem.
Okay, so we've thoroughly explored the NT-Febophore case. Let's move on to 5 points.
Okay, so with 5 points, Theorem 27 tells us that we can still choose the first camera center however we want. But now the second camera's position becomes uniquely determined.
Wait, so with just 1 extra point, we go from having infinitely many possibilities to just 1 location for that second camera.
You got it. It's a huge jump in constraint.
That's crazy. And how do we find that special point?
The paper introduces this really clever construction using intersecting conics.
Conics again. I'm sensing a theme here.
They're our trusty guide in this whole geometric journey. In this case, we construct 5 conics.
Okay.
Each one passing through 4 of the points in that second set. And the unique intersection point of all 5 conics, that's exactly where our second camera needs to be.
Like a geometric treasure hunt.
Yeah.
But why does this construction work?
It all comes down to those relationships between the 4-point cross ratios and the invariant properties of 5 points on that image line.
Okay.
Remember those bracket polynomials we were talking about?
Yes.
Well, they come back into play here. They establish those connections and show us that this intersecting conic construction isn't just some coincidence.
Right.
It's rooted in really deep mathematical principles.
So we're not just drawing lines and circles here.
No.
We're tapping into the fundamental structure of these points and how they're projected.
Exactly.
And what happens to our camera center's variety in this case.
With 5 points, C5 becomes a surface.
Okay.
It's a 2-dimensional object.
Right.
Still embedded in our 4-dimensional space. And Theorem 31 highlights its connection, something called Cremona transformations.
Cremona transformations, those sound intense.
They are. They're basically mappings between projective spaces that can stretch and twist things in some really interesting ways.
So it's like looking at our geometric problem through a funhouse mirror.
Yeah, exactly. And in this case, the projection of our camera center's variety onto either of the P2 planes actually turns out to be a Cremona transformation of degree 5. This transformation has special points called base points that play a key role.
Base points. So are these like anchors for the transformation?
Yeah, you could think of them that way.
Okay.
And what's interesting is that these base points, along with some exceptional points that pop up in that intersecting conic construction, are going to be really important for understanding the even more intricate case of 6 points.
Exceptional points, base points.
Yeah.
It sounds like we're gathering a whole cast of geometric characters here.
We are. And as we move to 6 and 7 points, these characters are going to play even more important roles.
Right. So on to 6 points. What new geometric twists can we expect?
So with 6 points, the invariant theory we talked about earlier really takes center stage. Remember those Joubert invariants?
Yeah, those special invariant polynomials.
Right.
That capture the essence of 6 points.
Exactly.
On the image line.
They're like our invariant signatures for 6 points in P1. And it turns out these Joubert invariants, when pulled back to P2, give us the equations for cubic curves that constrain our camera centers.
Hold on. So we're going from invariant polynomials to cubic curves. How does that leap happen?
A beautiful connection. Remember lemma 14?
Yeah, vaguely.
It lets us relate brackets in P1 to brackets in P2 by incorporating the camera center. So we take those Joubert invariants, which are written in terms of brackets in P1, and we basically replace each bracket with its counterpart in P2, including that camera center.
So we're lifting those invariants from the image line up to the plane.
Exactly.
And in doing so, we're introducing the camera center.
That's right. And these modified Joubert invariants, let's just call them A, B, C, D, E, and F, become our bridge to the cubic curves. It turns out these new polynomials, when evaluated at the points in our sets X and Y, satisfy a very specific set of equations called the Cremona hexahedral equations.
Cremona hexahedral equations. That sounds intense.
They have this really interesting geometric story to tell. These equations describe a cubic surface in P5. Remember those hypersurfaces we were talking about?
Right, so we're going up in dimensions again.
We are. But how does a cubic surface in P5 connect to our cubic curves in P2?
That's a good question.
Here's the key. There's a mapping from P2 to that cubic surface in P5.
Okay.
And this mapping is defined using those pulled back Joubert invariants A through F.
So each point in our plane gets mapped to a point on this cubic surface
Right.
in a higher dimensional space. And that mapping is guided by these special polynomials.
Exactly. And because our camera centers have to satisfy those Cremona hexahedral equations,
Right.
they have to lie on the image of this mapping,
Okay.
which turns out to be our cubic curves denoted as cx and psi.
So it's like we're taking a detour through a higher dimensional space just to understand those constraints on our camera placements back in Flatland.
Yeah, it's a wild ride.
It really is. And it explains why choosing a point on one cubic curve, cx, uniquely determines a point on the other cubic curve, cx.
Right.
They both correspond to the same point on that cubic surface in P5. It's like they're linked through this higher dimensional connection.
Exactly.
It's amazing to think that these simple camera placements in Flatland are governed by such complex relationships in these higher dimensions.
I know, it's really cool.
But the paper doesn't stop there.
Yeah.
They also give us a geometric way to construct these cubic curves
Yes.
using a variation of our trusty intersecting conic construction.
That's right. So you start by picking a point in your first set,
Okay.
X.
Okay.
For that point, we construct 5 conics,
There.
each passing through 5 of the points in X, including that special exceptional point we were discussing.
Right, those exceptional points are like echoes from our previous exploration.
Exactly. And those 5 conics intersect at a unique point, which is our exceptional point,
Okay.
corresponding to the chosen point in X. We repeat this for each of the 6 points in X.
How?
And that gives us 6 exceptional points.
So we're using conics to find these special exceptional points.
Exactly. And those 6 exceptional points, along with the original 6 points in X, completely determine the cubic curve CX. And then we just do the same for the set Y to find psi.
It's amazing how conics, these simple curves, are guiding us to these more complex cubic curves that are constraining our camera placements. And Theorem 35 sums all of this up, right? It describes the camera center's variety C6 for 6 points.
That's right. C6 is now a curve, a one-dimensional object still embedded in that 4-dimensional space. Theorem 5 tells us that this curve projects onto those cubic curves, Cx and psi.
So our camera center's variety has shrunk again. It went from a hypersurface to a surface, and now it's a curve.
That's a great observation. And as we'll see with 7 points,
Yeah.
this trend of shrinking keeps going,
Okay.
showing just how the constraints on camera placements increase as we keep adding more points.
All right, on to the final act. 7 points. What happens in this grand finale?
Okay, so for 7 points, our camera center's variety, which we call C7, becomes a finite set of points.
A finite set. So we go from infinitely many possibilities down to just a handful of specific locations.
You got it. It's like those camera placements are completely cornered.
And the paper gives us a way to actually find these special points.
Oh, it does. And it involves those cubic curves that we just talked about.
So those cubits are bad. I'm sensing a grand geometric finale here.
You got it. We start by choosing any 2 6-point subsets from our set of 7 points. It's like we're temporarily ignoring 1 point at a time.
Okay.
For each of those 6-point subsets,
Yeah.
we construct the cubic curves,
Okay.
just like we did in the 6-point case.
So you have 2 sets of 6 points, each with its own set of cubic curves.
Right.
What do we do with them?
So these 2 cubics will intersect at 9 points.
Okay.
But 6 of those intersection points are kind of just artifacts of the way we constructed it.
Okay.
They correspond to the 5 points that are common to both subsets and their associated exceptional point.
Okay.
The 3 remaining points.
Yeah.
Those are our potential camera centers.
So it's like sifting through the geometric debris to find those hidden gems.
Yeah.
Our camera centers.
I like that. And the paper also offers a different way to find these camera centers using conics.
Conics again. They really are the stars of the show.
They really are.
Yeah.
So for 7 points, the space of fundamental matrices that work for our problem is denoted LXY,
Right.
and it's a one-dimensional space.
Okay.
This means any fundamental matrix in LXY can be expressed as a linear combination of 2 specific fundamental matrices, F1 and F2.
Okay.
Using this representation,
Yeah.
we can actually derive 3 quadratic equations that constrain that camera center. These equations define 3 conics.
Okay.
And where those 3 conics intersect, that's where our possible camera centers are.
So we have 2 paths leading to the same destination. Intersecting cubics or intersecting conics.
Exactly.
Both guiding us to those elusive camera center locations.
That's right. And Theorem 6 summarizes all of this, stating that there are at most 3 possible camera placements for 7 points.
So we went from infinite possibilities down to just 3. It's
Yeah.
amazing how adding just a few points just drastically reduces our freedom of placement.
It really does. And our camera center's variety, C7, reflects this.
Right.
It has shrunk down to just a set of 3 isolated points.
They're like the last survivors of this geometric shrinking game.
Exactly. And when the coordinates of our points are rational numbers, those 3 camera center points will also have rational coordinates.
So even though we're dealing with all these complex geometric constructions,
Yeah.
we can still find solutions that are in that familiar world of rational numbers.
And there's an even deeper layer here. Those conics that define those camera centers actually contain infinitely many rational points.
Infinitely many. But we only have 3 camera centers as solutions.
That's true, but those 3 solutions are like gateways to these infinite families of rational points.
Okay.
These points all lie on the conics.
Right.
And they satisfy the constraints of the problem even though they're not our specific camera centers.
So it's like our finite solution set has this hidden structure.
Yeah.
These infinite families of rational points that are giving us even more insights into the geometry of the problem.
Exactly. So with that, we've explored all of our cases. 4, 5, 6, and 7 points.
Right.
Each revealing a unique interplay between geometry, constraints, and those invariant properties.
It's been a wild ride through the world of flatland geometry, but my brain is a little bit overloaded.
I hear you.
In the next part, let's try to summarize the key takeaways and maybe venture a guess at what questions this paper leaves us pondering.
Yeah, let's take a step back and see what we've learned.
All right, so let's try and bring all of this together. We've gone pretty deep into flatland, exploring how cameras would capture images in this two-dimensional world.
It's been a fun ride.
It has. We even ventured into those higher dimensions with projective geometry
Maybe.
and explored those invariant properties that stay constant no matter how we change our perspective.
Yeah, invariant theory is always fascinating.
It is.
The way it helps us understand the core structure of these problems is really cool.
Yeah, and I think what's so amazing about this paper is how it connects these seemingly simple geometric ideas to some pretty profound concepts in computer vision.
Right.
Remember that the original question was, when can 2 sets of points in completely different planes be projected onto the same line so that those images look the same?
Right. It's like asking if 2 different flatland cameras, each looking at a different scene,
Right.
could create the exact same picture.
And theorem 2 is pretty mind-blowing. It basically said that those projections can only be identical if the 2 sets of points are projections of the same set of points in a higher dimensional space, P3.
Exactly. Like those points in flatland are just shadows cast by the same 3D object.
And that connection to 3D reconstruction that's massive. It's a core problem in computer vision.
Absolutely.
Self-driving cars, 3D modeling, even medical imaging. This paper shows us that even in a simplified 2D setting, those same core challenges and insights apply.
It's amazing how these connections appear in unexpected places.
Mhm.
And the paper doesn't just stop at proving that these projections exist.
Right.
It delves into actually characterizing those special camera placements, those projection centers,
Right.
that make those identical images possible.
And those tools from invariant theory were so important for that, right?
Oh, for sure.
The bracket polynomials, Kempe's theorem,
Mm-hmm.
the camera center's variety. They give us a whole new way to understand the constraints on those camera placements.
Exactly. And as we explored the specific cases with more and more points, we saw how that camera center's variety actually shrank,
Right.
showing how the constraints increased. It was like those possibilities were literally closing in.
Yeah, it was super cool to see how conics and cubics kept reappearing as those key players.
They're such fundamental shapes in geometry.
Right. They weren't just some abstract shapes. They were literally guiding us to those special camera placements.
And even those more complex concepts like Cremona transformations, those mappings that can warp space,
Yeah, they were intense.
they were. But they helped us reveal even deeper structure within this problem. It really shows how interconnected different areas of math can be.
And it's wild to think that even though this problem is rooted in this imaginary world of flatland, the insights and techniques we learned have real-world applications in computer vision. It reminds us that exploring these abstract ideas can lead to some pretty tangible advancements.
I completely agree. That's one of the most rewarding parts of math, that ability to bridge the gap between the theoretical and the practical.
Looking back on all of this, what would you say is the key takeaway you'd want listeners to walk away with?
I definitely say it's the power of understanding invariant properties.
Right.
By focusing on those things that remain constant, even as our perspective shifts,
Right.
we can unlock some really deep insights into the structure of these geometric problems and even connect those insights to real-world situations.
And for me, it was the realization that even something that seems like a simple geometric question
Right.
can lead to a surprisingly profound mathematical journey.
It really can. And it just shows how curiosity and a willingness to explore can lead to unexpected and fascinating discoveries.
As we wrap things up, what's a question that this paper has left you pondering, something that we didn't explicitly talk about, but that you'd be interested in looking into further?
Yeah, that's a good question. For me, I think it would be the idea of continuous camera movement in flatland.
Okay.
If our cameras could move along paths,
Right.
what would those paths of valid camera placements actually look like for different numbers of points?
Oh, wow. That's a great question.
Hmm.
So we're adding a dynamic element to this otherwise static geometric problem.
Exactly. Would those paths just be smooth curves? Or would they be isolated points? Or even something more exotic? And how would the shapes of those paths change as we move those points around?
It's like opening up a whole new avenue of exploration,
Exactly.
connecting geometry to topology and dynamics.
I love that.
Yeah, it seems like every answer in flatland geometry just leads to more intriguing questions.
It always does.
And that's the beauty of math.
Yeah.
It's an endless journey of discovery.
I agree.
Well, thank you so much for joining us on this flatland adventure.
It was fun.
It was. Until next time, keep exploring, keep asking those questions, and keep pushing those boundaries of knowledge.
Couldn't have said it better myself.
We'll see you on the next deep dive into the fascinating world of ideas. All right, folks, get ready for a wild ride. Today, we're going to take a deep dive into projective geometry and computer vision.
Sounds exciting.
Yeah, but get this. Imagine we're actually robots living in flatland,
Flatland, I like it.
a two-dimensional universe, right? And we have cameras.
All right.
Could we have two different scenes seen from different spots that actually create the exact same image?
That's a really cool question, and it kind of gets to the heart of some really fundamental principles in both projective geometry and computer vision, right? It's like we take for granted that our 3D world projects onto our 2D retinas.
Right.
But what happens when you have a 2D world projecting onto a 1D image?
Exactly.
That's fascinating.
And to help us unpack this mind-bending problem, we're diving into this paper by Agarwal, Connolly, Cornell, Duff, and Thomas.
Oh, nice.
They lay out this challenge.
Yeah.
They want to figure out when two sets of points in separate projective planes can project onto the same image on a projective line. So it's like this puzzle, but with serious implications for how we understand vision.
Absolutely. And they don't just tell us if it's possible, they go deep into the HOW.
Yeah.
They explore all the geometric conditions, the constraints. They even give us specific constructions. And that's where that proof section of the paper really shines.
Right.
We're going to get to dissect those proofs and unravel that logic and the geometric insights they reveal.
Okay, so the paper's abstract kind of sets the stage, right? We're dealing with sets of labeled points in two separate projective planes.
Oh, right.
And we want to know when they can be projected onto that same image, but on a projective line. Sounds simple enough.
Sounds simple enough.
But I have a feeling things are about to get wonderfully complex.
Oh, you bet. But before we jump into those theorems and proofs, let's make sure we're all on the same page with some basic concepts here.
Okay.
We're in projective space,
right,
denoted as K. It's our mathematical playground, so to speak, where points aren't just fixed locations. They're represented by those equivalence classes of non-zero vectors.
Right. So in sub 2 sub, our flatland, the point 1, 2, 3, is the same as 2, 4, 6 because they're just scalar multiples of each other.
Precisely. It's all about those ratios and proportions.
Yeah.
All right. Now, what about our camera?
Okay.
In this context, it's not like a physical device.
Right.
It's a mathematical function. It's a full rank linear projection that takes us from that higher dimensional projective space down to a lower dimensional one. It's like shining a light and seeing the shadow of our flatland world on a line.
That's a great visual. And that brings us to the center of projection, right?
Yeah.
It's like the vantage point of our imaginary camera.
Exactly.
But the paper emphasizes that it's a projective invariant. What's so important about that?
So it means No matter how you mess with the projection using those projective transformations, the center of projection stays put. It's a fixed point in all that, in that whirlwind of transformations. Unlike the specific camera matrix, which can change.
No.
Depending on your coordinate system, the center itself is a
Yes, sir.
fundamental geometric property of the projection.
Okay, so it's like a rock in a stormy sea. It holds its ground no matter what. But how does that invariance affect our ability to analyze these projections?
That's a fantastic question. So that invariance allows us to really focus on those essential geometric relationships
Yeah.
between the points and the camera center without getting bogged down by the specific algebraic representation of it. It kind of simplifies our analysis and allows us to derive those results that hold true regardless of how we choose to represent our projective spaces.
So Theorem 2 lays out these conditions for when those projections are even possible. What does it tell us?
So Theorem 2 says that two sets of points, let's say in sub 2 sub,
Okay.
can have the same image in sub sub if and only if they themselves are projections of the same set of points from a higher dimensional space.
Okay.
In this case, sub's 3 sub.
So like those shadow puppets, two different shapes can cast the same shadow if you position the light source just right.
Exactly.
Okay, so the higher dimensional space is like the source.
Yeah.
And those points get projected down to our flatland planes,
Yeah.
creating those sets X and Y.
Right.
And if those sets come from that same source in sub 3 sub, then we can find camera positions that make them project onto the same 1D image.
Exactly.
It's a fundamental connection.
And the paper doesn't just state this. The proof dives into actually constructing those camera matrices
Right.
and showing how the projections work out.
Oh, cool.
It gets into the nitty-gritty of the matrix operations, how the points transform.
Wow.
So it rigorously demonstrates that this relationship between 2D and 3D
Yeah.
isn't just a coincidence, it's a geometric necessity.
I love that we're not just accepting things at face value.
I agree.
We're diving into these proofs to really understand why these connections exist.
Yes. It's about going beyond the what and
Yeah.
getting to that why.
Exactly.
And that's going to be crucial as we move forward and encounter even more complex concepts and constructions.
So how do we actually check if two sets of points can be projected onto the same image?
Right.
Theorem 4 introduces the fundamental matrix, or F. What's the deal with this matrix?
Yeah, the fundamental matrix is a really powerful tool
Okay.
because it captures the relationship between corresponding points in two images, even if we don't know that 3D scene or
Right.
those camera positions.
Okay.
Theorem 4 tells us that two sets of points can be projected onto the same image if and only if there exists
Okay.
a rank 2 matrix, this F,
Right.
that satisfies some very specific conditions.
So F acts as this bridge between the projections and the geometry of the points, right? What are those conditions?
Okay, so first, the right and left null spaces of F have to be spanned by the centers of projection,
Right.
our camera positions A and B.
Okay.
So this tells us that F is encoding information about where those cameras are located
Right.
relative to the points.
Gotcha.
Second, for any pair of corresponding points, X and Y, from our two sets, E sub X has to equal 0. This condition links F to what we call the epipolar geometry of the projections, essentially saying that corresponding points must lie on corresponding epipolar lines.
Okay, so F is like a detective,
Yes.
holding clues about both the camera positions and the correspondences between those points in the images.
Exactly. You got it.
But how do we interpret it geometrically?
Okay, so imagine you draw a line from a point in the first plane through the camera center A.
Okay.
This line's going to intersect the second plane.
Yeah.
And the point of intersection will lie on a specific line in that second plane called the epipolar line.
Okay.
This epipolar line is determined by F and that original point.
Right.
Essentially, F is mapping points to lines.
Okay.
And these lines are capturing the geometry of the projections.
So F is encoding the geometry of the epipolar lines,
Yeah.
which tell us how points in one image relate to points in the other image, even if we don't know anything about that 3D scene.
Exactly.
That created those images.
And the proof of Theorem 4, of course, goes into the details of constructing this matrix
Yeah.
and proving that it satisfies those conditions if and only if those projections are even possible.
Oh, wow.
It involves, manipulating the camera matrices,
Right.
using those properties of projective transformations, carefully analyzing those relationships between the points and their projections.
Oh, cool.
So it's a beautiful dance between algebra and geometry.
I love it. So we've got this powerful tool, F, to analyze our projections.
Yeah.
But then they bring in Grassmann tensors. What are those?
Okay, so think of Grassmann tensors as a generalization of that fundamental matrix
Okay.
to higher dimensions. They capture that same kind of epipolar geometry,
Right.
but allow us to analyze projections in spaces beyond our 2D flatland.
So are we saying that these ideas about cameras and projections in Flatland
Yes.
have implications for understanding vision in our 3D world?
Absolutely. The principles we're uncovering here, even in this simplified 2D world, they provide a foundation for understanding how 3D scenes project onto 2D images.
Oh.
And they give us insights into concepts like, epipolar geometry, camera calibration, and even 3D reconstruction, which are essential for all those computer vision applications like robotics, autonomous driving, even medical imaging.
That's what's so fascinating.
Yeah.
We're starting with a simple problem in Flatland, but it has far-reaching implications.
Yes.
What if we have more than two sets of points?
Right.
Things get trickier.
Of course, they always do.
Theorem 6 seems to tackle this.
Yes, it does.
What's the takeaway?
So Theorem 6 tells us that finding cameras for multiple sets of points is possible if and only if we can find pairwise compatible fundamental matrices. Each pair of sets needs an F that satisfies those conditions we talked about earlier. But even if we find those compatible Fs, it doesn't guarantee that we can reconstruct that 3D scene.
Why not? If each pair could be projected onto the same image, shouldn't they all fit together somehow?
Not necessarily. To reconstruct a 3D scene,
Right.
we need more than just pairwise compatibility. We need global consistency. Imagine you have 3 sets of points.
Okay.
You find compatible fundamental matrices for sets 1 and 2, sets 2 and 3, and sets 1 and 3. That doesn't mean all 3 can be projected onto the same 1D image simultaneously.
Ah, okay. So it's like having puzzle pieces that fit in pairs.
Yes.
But they might not form a complete picture.
Exactly. That's a great analogy.
There might be some inherent incompatibility.
Yeah, and the paper mentions radial cameras as a potential way to achieve that global consistency. But that's a whole other deep dive for another day.
All right, so we might not always be able to reconstruct the full 3D scene.
Right.
But we're learning a lot about the constraints and relationships between these sets of points and their projections.
Yes.
We know when it's possible. We've got a tool to check for compatibility. And we're seeing the limits of what's achievable.
That's a great summary.
So we tackled question I, figuring out when those special projections are possible. Now let's dive into question 2.
Yes.
The exciting challenge of finding out where those cameras can actually be placed.
All right. It's time for a geometric treasure hunt.
I'm ready. What tools are we going to use?
We're going to venture into the world of invariant theory. Don't let the name scare you.
Okay.
It's really just a powerful way to understand how things behave under transformations.
Oh.
And in our case, it'll help us describe that locus of camera centers, the special points A and B.
So instead of just checking for the existence, we're going to get a blueprint of where they can be.
Exactly.
What's the first landmark?
All right, so the paper introduces this concept of what they call the camera centers variety, denoted as CN. This is our playground for question 2.
Right.
Think of it as a set of all possible camera positions, A and B, that are consistent with our 2 sets of n-labeled points, x and y. It exists in sub2 sub x sub 2 sub, which is essentially a space where each point represents a possible combination of camera positions.
So each point in this variety corresponds to a specific set of camera placements that could produce the same image from our original point sets.
Exactly. And what makes this variety even more powerful is it comes with 2 projections.
Okay.
We can project a point in the variety onto either of the sub2 subspaces, giving us the location of camera A or B.
Oh, cool.
This is going to be our guide as we explore the geometry of camera placement.
Okay, I'm starting to see how this variety acts like a map.
Exactly.
Guiding us through all the possible camera positions.
Yes.
But where does the fundamental matrix F fit into this?
Oh, it's so crucial. So we can think of the camera centers variety as a projection of a higher dimensional variety that includes F. The paper calls this variety FCXY.
Okay.
It consists of all triples, FAB, that satisfy those conditions we talked about in Theorem 4. Our camera centers variety, CXY, is just a shadow of this bigger variety, keeping only the camera positions, A, B, and discarding F.
Okay, so we're using F as a stepping stone, connecting the geometry of those corresponding points to the possible camera positions.
Absolutely. It acts like a bridge. Now, here's where things get a little more fascinating.
Okay.
These varieties, FCXY and CXY, are part of families of varieties.
Oh.
Think of them as collections of similar geometric objects.
Right.
The properties of these families depend on the number of points that we're dealing with.
So the size of our point sets influences the shape and structure
Yes.
of these varieties.
Exactly.
So we need to analyze each case separately.
Well, not entirely. Thankfully, there are some consistent patterns. For a given then, a lot of properties of these varieties, like their dimension, their multi-degrees, even the structure of their defining equations remain the same for a large set of what we call generic choices of x and y. This allows us to talk about FCN and CN as like representatives of these families without getting too bogged down in the specifics of every single configuration.
So we're looking for general principles rather than getting stuck in the specifics.
Yeah.
Why is this generic property important?
Because it lets us focus on the underlying geometric structure of the problem.
Right.
So for a given n, there's a certainly typical behavior for the camera center's variety. Of course, there might be some special cases where things are different, but those are exceptions, not the rule.
So we're creating a roadmap, and this helps us draw those main highways.
Exactly. A great analogy.
Okay.
Now, Lemma 17 gives us a crucial piece of information about the dimensions of these varieties.
Okay.
Get this. If we have 8 or more points, both FCN and CN are empty, meaning there are NO camera pairs that can produce the same image for that many points.
So there's a limit.
There's a fundamental limit to how many points we can project and still find matching camera positions. It's a key takeaway.
Wow.
We can only have solutions to our problem for up to 7 points. Beyond that, the geometry says no.
That's wild.
Yeah, it leads us to corollary 18, which states that for n greater than or equal to 8, there's no camera pair that can project our sets onto the same image.
8 or more, and it's game over.
Exactly.
No matching images. That's a pretty powerful constraint.
It is.
What's so special about 7?
That's an excellent question. And to be honest, it's something the paper doesn't explicitly address.
Oh, okay.
But it just highlights that open-ended nature of mathematical inquiry, right?
Right.
Even after proving a result, there are always more questions to ask, deeper layers to explore.
I love that. Before we jump into those cases,
Yeah.
there's one more concept we should talk about.
Okay.
Multi-degrees.
Multi-degrees, yes. Think of them as a way to measure the complexity of these varieties. Imagine you're slicing CN with lines from each of the sub-2 subspaces. The multi-degree tells you how many points of intersection you'll get.
So it's like quantifying how complex these varieties are. More complex varieties means they intersect with those lines at more points.
Exactly. And these multi-degrees are going to be super important as we explore those specific cases. We'll see how they change as we add more points, and it'll give us a sense of how the complexity of the problem is changing.
I'm ready to see how all these pieces fit together.
Yes.
The varieties, the fundamental matrices, the multi-degrees, and those elusive camera positions.
It's going to be a fun ride.
I can't wait.
Me too. All right. Are you ready to tackle NCL 4?
I think so.
This is where it gets interesting.
Okay.
Remember, any 3 points in subset can be mapped to any other 3 points using a homography.
Right, right. So with 4 points, the arrangement actually matters.
Exactly. Theorem 20 dives into this case.
Okay.
And it says one of the camera centers can be chosen freely.
So we have some flexibility.
We have some freedom.
Where we place the first camera.
Yeah. But what about the second camera? Is it also free roam?
Good question.
Not quite. Once we fix that first camera, A, the second camera, B, has to lie on a specific conic.
A conic.
And not just any conic.
Right.
This one has to have a very specific conic cross ratio.
Conic cross ratio. Yeah, could you remind me what that is?
Okay, so imagine you have 4 points on a conic.
Okay.
You draw lines from one point to the other 3, and then you draw a line that intersects all those lines, like a transversal.
Okay.
The conic cross ratio is a number that captures the relative positions of those 4 points on the conic.
All right.
It's determined by the ratios of the distances between the points where those lines from the first point intersect the transversal.
Gotcha. So it's like a measure of how spread out or bunched up those 4 points are on the conic.
Exactly.
And Theorem 20 is saying that the conic cross ratio of those projected points from the second camera has to match the conic cross ratio of those original 4 points in Y.
Precisely. It's this beautiful connection
Yeah.
between the arrangement of the points and the constraints on where we can put those cameras.
Wow.
It's not enough for the points to just project onto the same line.
Right.
Their relative positions, as captured by that cross ratio,
Okay.
also have to match.
So can we visualize how to find this conic?
Absolutely. That's where figure 4 comes in.
Okay.
In the paper, it gives us a step-by-step construction.
Oh, cool.
And it's pretty intuitive.
Let's walk through it. What's the first step?
Okay. We start by just choosing a point
Okay.
for our first camera, A,
Okay.
and a projection line in the first plane.
Right.
Then we project our 4 points from set X onto that line through A.
So like shining a light from A and seeing where the shadows fall.
Exactly. Now, in the second plane, we use those projected points and the first 2 points from set Y to find a special point called the center of perspectivity.
Ooh, that sounds cool.
Yeah, it's the point where lines connecting corresponding projected points and points from Y intersect.
Okay.
It's the point from which those 2 sets of points appear to be in perspective with each other.
Like a vanishing point?
Exactly, like in a perspective drawing.
Oh, that's a good analogy.
Yeah.
So this helps us align the 2 sets.
It does. It lets us find the second camera's projection line in the second plane. Once we have that line, we can determine the other 2 projected points, making sure they have the same cross ratio.
So matching cross ratios.
Yes.
All thanks to this center of perspectivity.
Yes. What's the final step?
Let's find that second camera.
Okay, so we just connect the corresponding projected points and the original points in Y. The point where those lines intersect, that's our B.
That's beautiful.
And it gets even better.
Does it?
This construction shows us that the locus of all possible positions for B, for a fixed A, forms a conic itself.
A conic.
Yeah, that's what Theorem 26 is telling us about C sub 4 sub.
So we've uncovered a whole curve
Yes.
of possible positions.
Exactly. Options, but within a very specific constraint.
Like a geometric dance.
I like that. Theorem 26 tells us even more. C sub 4 sub is a hypersurface in sub 2 sub, sub 2 sub.
Okay.
It's a 3-dimensional object embedded in 6-dimensional space.
All right, that sounds complicated.
It just means those camera pairings have a certain richness to them.
So it's not just a tiny sliver of possibilities.
No, not at all.
There's a whole 3D space of camera configurations that work.
Exactly. And the projections of C sub 4 sub onto either sub 2 sub cover the entire plane. Right. So you can put one camera anywhere and you'll find a corresponding position for the other.
Oh, that's neat.
And C sub 4 sub has a bidegree of 2, 2, reflecting that geometric complexity.
Okay, ready to add another point?
Let's do it.
See what happens with NL5.
Buckle up. We're entering the world of Cremona transformations.
Cremona transformations. Okay, so what changes with this 5th point?
The invariant theory gets more intricate.
Okay.
We need those 6 bracket monomials, M sub 1 sub through M sub 6 sub. Remember those?
Yeah, they capture the relationships between pairs of points.
Exactly. They're like a shorthand for the geometric arrangement.
Right.
So how do they help us with N5? Well, they form the basis of our invariant vector, G.
Okay.
This vector, with components based on those monomials, lets us compare different sets of points.
Right.
Lemma 13 says 2 sets of points can be transformed into each other using those SL2 transformations, if and only if their invariant vectors are scalar multiples of each other.
So like fingerprints, if they match, the sets are the same, just from different perspectives.
Exactly. But remember, we're dealing with points in sub 2 sub, not sub sub. How do we connect these invariant vectors, which are based on brackets in sub 2 camera centers in sub 2 sub?
Yeah, how do we do that?
That's where lemma 14 comes in. It's our bridge between the 2 spaces.
Oh, nice.
It says that if you have a camera projecting points from sub 2 sub to sub sub, the brackets in sub sub are proportional to brackets in sub 2 sub that involve the camera center.
So we can pull back those brackets
and
incorporate the camera center.
Exactly.
What does Theorem 27 tell us about the n equals 5 case?
Okay, so similar to N4, we can choose A freely.
Okay.
But here's the twist.
Okay.
The second camera center B is now uniquely determined.
No more conic of possibilities.
It's down to a single point.
Wow. How do we find it?
Through what's called an intersecting conic construction.
Okay, I like it already.
We consider 5 conics.
Okay.
Each one passes through 4 points in Y, leaving out a different point each time. These conics are determined by matching their cross ratios to the projections from the first camera.
So we're doing 5 n equals 4 constructions.
Exactly. And those 5 conics will intersect at a single point.
That's our second camera.
You got it.
That's elegant.
Now, how do we find that intersection in practice?
Yeah, good question.
Cremona transformations.
Okay, tell me more.
Cremona transformations are these special functions that map a plane to itself, but not in a simple linear way. They warp the plane.
Oh, wow.
The one we're interested in is the quadratic Cremona transformation, denoted as FQ.
Right.
FQ can take 2 conics that share 3 points and transform them into 2 lines. Those lines will intersect at a point that's related to the 4th intersection point of the original conics.
So we're straightening out the conics.
Exactly. By applying FQ to a pair of our conics, finding the intersection, and then transforming back, we get that intersection point.
That's cool.
Theorem 31 gives us even more insight. C sub 5 sub, our camera center's variety, is a 2-dimensional surface. It projects onto each plane, covering the whole space. And those projections have rational inverses.
So we can go back and forth.
Yes.
Between camera positions in the 2 planes using rational functions.
That's right. Here's the cool part.
The
map that takes you from A to B is a Cremona transformation.
Cremona transformations are everywhere.
Right. But this time, it's degree 5. A step up in complexity. Theorem 31 also tells us the multi-degrees of C sub 5 sub are 1, 5, 1. More complex than C sub 4 sub. Makes sense, right?
Yeah, makes sense.
We added a point.
Right.
To understand these degree 5 Cremona transformations even better, we'll need base points and the homoloidal net.
Okay, what are base points?
Think of them as special points where the Cremona transformation might be undefined or behave strangely.
So they're points where things get weird.
Basically. The homoloidal net is a family of curves associated with the transformation. You get them by setting a linear combination of the transformation's component functions to 0. The base points lie on all the curves in the family.
So the homoloidal net is like a fingerprint.
Exactly. Proposition 32 links the degree of the transformation to the multiplicities of its base points.
So a higher degree means more base points.
Or base points with higher multiplicities. More powerful transformation.
Right.
Now, for our degree 5 Cremona transformation in N5, Theorem 33 says it has 6 base points.
6.
Each with a multiplicity of 2. 5 are the points in X, but the 6th one is a exceptional point.
Exceptional point.
Exceptional point.
Okay, what's so special about it?
It's not in our original points, but it comes from the transformation. It's a function of the 5 points in X. Equation 44 gives us a formula for X, and there's another one, E in the image plane.
2 exceptional points.
Related to X. These will be important for NX6.
Okay, so they're lurking behind the scenes.
They are.
Influencing the Cremona transformation. What happens as we add more points?
They become crucial. These exceptional points, together with the originals in X and Y, define special conics that help constrain the camera positions.
Oh, interesting. As we add more points, new tools emerge.
Exactly.
Can't wait to see NE6.
All right, get ready for NE6. This is where the invariant theory gets really interesting.
I'm excited.
We've got Joubert invariants, more Cremona transformations, and a whole web of geometric relationships.
Joubert invariants, those sound intense.
They are pretty cool. Theorem 34 tells us that with 6 points, our camera centers A and B are no longer free to roam. They're now confined to cubic curves.
Cubic curves?
Yeah, these elegant curves defined by degree 3 polynomials. We'll call them Cx and Psi. And they pass through those 6 points in X and Y, respectively.
So we've gone from a single point in NA5 to a whole curve. More freedom, but still constrained.
Exactly. It's like the cameras are on a guided tour. But how do we find these curves?
That's a good question.
That's where those Joubert invariants come in.
Okay, remind me about those.
Remember our bracket monomials, M sub 1 sub through M sub 6 sub?
Yeah, they capture those relationships between the points.
Right.
Yeah.
We combine them in a special way to create 6 values. The Joubert invariants. A, B, C, D, E, and F.
So they're like a higher level fingerprint.
Exactly. Capturing those relationships between 6 points.
So how do we use them?
Well, just like those invariant vectors, these invariants help us compare configurations. We pull them back to sup to sup using lemma 14. We get 6 cubic polynomials shown in equation 50.
I'm starting to see those cubic curves. The camera centers have to be chosen so those polynomials are 0.
Precisely. Those polynomials are like equations of motion for the camera.
I like that. The paper also mentions Cremona hexahedral equations. What are those?
There are three equations that define a special cubic surface in SUP5 sub.
A higher dimensional space.
Yes, but it holds a key to understanding our camera centers.
Okay, how so?
When we evaluate our 6 cubic polynomials at camera center A,
Yeah.
and use those values as coordinates in SUP5 sub,
Okay.
the resulting point lies on this hexahedral surface.
Oh, wow. So it's like a secret code those camera positions have to follow.
Exactly. And if we swap x and y, we get another set of polynomials and a corresponding surface.
So both camera centers have to lie on specific curves.
Yes, determined by the points and those Joubert invariants.
But Theorem 34 also says that once we fix A, B is unique. Why is that?
Because the map from SUP to that hexahedral surface
Okay.
is 1-to-1, except at the original 6 points.
Okay.
So there's only 1 point on that second surface, and
Right.
therefore only 1 point on side that satisfies the same equation.
That's our camera center B.
You got it.
Amazing. It's like those surfaces are matchmakers, pairing up the camera centers.
I love that analogy. And remember those exceptional points from n equaled 5?
The ones that weren't in the original sets.
Yeah, they're back.
Okay.
We can construct Cx and psi using those exceptional points and some conics.
So 2 paths to the same destination, an algebraic one and a geometric one.
Exactly. The paper shows how to construct 6 exceptional points in each plane.
Okay.
The cubic curves are then determined by passing through those points.
So those exceptional points are like anchors.
Perfect way to put it. Theorem 35 summarizes n equals 6. C sub 6 sub is a curve in SUP2 SUP.
Okay.
Its multi-degrees are 3, 3.
All right.
So it's projected onto those cubic curves.
Okay. On to NN7, the final challenge.
Yes.
Does the complexity keep increasing?
Actually, there's a simple construction to find those camera centers. We only need 2 cubic curves.
Only 2. That sounds easier than I expected.
Right. We choose 2 6-point subsets from our 7 points.
Okay.
For each subset, we construct those cubic curves.
We're using the NN6 solution.
Exactly. Those 2 curves will intersect in 9 points. Okay. But only 3 are valid camera centers.
So the geometry is guiding us.
Yes. And here's the interesting part. While those cubics get us to the camera centers,
Okay.
they're not the simplest equations.
Really?
Yeah, the vanishing ideal of C sub 7 sub actually involves conics.
Conics, hiding beneath those cubics.
Theorem 36 says both camera centers have to lie on the intersection of 3 conics each.
Okay.
And those conics intersect in exactly 3 points.
Our camera centers.
You got it. And to tie it all together, those 3 centers are also the base points of a quadratic Cremona transformation.
Cremona transformations are everywhere.
They are, mapping those 7 points onto each other.
I'm amazed by all the connections we've uncovered. From a simple question about flatland cameras, we've explored so much geometry: projective space, fundamental matrices, cross ratios, conics, Cremona transformations, invariant theory, exceptional points. It's incredible how it all fits together.
I know, right? It's a testament to the elegance of mathematics.
Exactly. And it doesn't end here. Imagine tackling this in sub-3 SUP or even higher dimensions.
Right. What new structures would we find?
It's mind-blowing. Who knew flatland cameras could lead us to such a deep exploration of geometry?
It's the power of mathematical thinking, to abstract, to generalize, to uncover those hidden patterns.
Thank you for joining us on this deep dive. We've uncovered the secrets of Flatland Vision. Keep those mathematical minds curious. Welcome to the deep dive. Today, we're going to be stepping into a world that's both familiar and strange, the world of Flatland. But instead of social commentary, we're diving into a fascinating computer vision problem that has some surprising mathematical depth. Imagine robots with cameras exploring a 2D landscape. Now, the question that's going to guide our deep dive today is this: can 2 different cameras in Flatland capture the same image of 2 different scenes?
That's a great question, and it's one that might seem simple at first. But as we dig deeper, you'll see it unveils a world of projective geometry, linear algebra, and even invariant theory.
Exactly. We've got a research paper here that tackles this very problem, and I have to say, it's a real head-scratcher. So to guide us through this mathematical maze, I've got an expert in all things geometry and algebra with us today.
Happy to be here. I think what's so captivating about this problem is how it connects these different mathematical fields in such unexpected ways.
Absolutely. So let's start with the basics. Can you kind of paint a picture for our listeners of the problem we're trying to solve?
Sure. Imagine two sets of points scattered across our 2D flatland. Our challenge is to figure out if we can position two cameras in this plane so that when they project these points onto a line, they both produce the same image.
Okay, so it's like having two separate scenes, but somehow the camera footage ends up looking identical. We're trying to find those camera sweet spots that make that illusion possible.
Precisely. Now, the research paper gives us a kind of mind-boggling answer to this question. It turns out that those two camera positions exist if and only if the two sets of points themselves are actually projections of a single common set of points in 3D space.
Wait a minute. 3D space? But we're talking about Flatland, a world of two dimensions. It's like we're suddenly discovering a hidden dimension.
That's exactly what's so intriguing about this. It connects different dimensions in a way that you wouldn't initially expect. And the key to unlocking this connection is something called the fundamental matrix.
Ah, yes, the fundamental matrix. I feel like that pops up all over computer vision.
Yeah.
But before we dive into that, let's clarify the problem setup a bit. We have two sets of points, right? Labeled as x sub b sub and x c sub in the plane. Each set represents a different scene.
Right.
And we're looking for two cameras, let's call them camera A and camera B, that project these points onto a line, creating the same image. Is that right?
Exactly. And the paper uses this notation sup2 sup to refer to the projective plane, which is our flatland in this case. The image line is represented as sup1 sup, which is essentially a projective line. And those cameras, they're represented as 3x2 matrices, which we can denote as A and B.
Okay, so far so good. Now let's talk about that fundamental matrix. What role does it play in connecting these cameras in these point sets?
So the fundamental matrix, often denoted as F, is a 3x3 matrix that encapsulates the geometric relationship between the two cameras and the points in the scenes. It's kind of like a bridge that links corresponding points in the two images, you know?
So if I understand correctly, if two points in different images correspond to the same point in 3D space, even if their 2D projections look different, the fundamental matrix can help us identify that connection.
Exactly. It's based on something called the epipolar constraint, which essentially says that for any point in one image, its corresponding point in the other image must lie on a specific line called the epipolar line. And the fundamental matrix, it defines these epipolar lines.
Okay, starting to make some sense now. So let's say we have our fundamental matrix. How do we actually use it to figure out where those cameras can be?
Well, the paper delves into the nitty-gritty details of how to construct this fundamental matrix. It involves some linear algebra, specifically using the camera matrices A and B. But once we have F, it gives us some really powerful constraints on those camera positions.
Okay, I'm all ears. How does it constrain those positions?
The paper basically says that the centers of projection for the two cameras, the points where those cameras are located, they must lie in the null spaces of F and its transpose, respectively.
Hold on, null spaces. For our listener who might not be as familiar with linear algebra, could you just give a super quick recap of what those are?
Of course. The null space of a matrix is basically the set of all vectors that, when multiplied by that matrix, result in the zero vector. In our case, the null space of F gives us all the possible positions for camera A, and the null space of F transpose gives us the possibilities for camera B.
So the fundamental matrix kind of acts like a filter. And these null spaces, they kind of pinpoint those special locations where the camera centers can hide. Is that right?
You got it. And the dimensions of those null spaces, how big they are, tell us how much freedom we have in placing the cameras.
So the bigger the null space, the more wiggle room the cameras have.
Exactly. Now, the paper breaks down the possibilities based on the number of points we have in our scenes. Things get really interesting when we start adding more points. It's like a game where each additional point adds a new rule that constrains those camera positions further.
Okay, I'm already on the edge of my seat. Tell me, how does the number of points change the game?
Well, with fewer than 4 points in each set, the cameras have a lot of freedom. They can practically be anywhere, and we can still find a way to make the images match. It's like having a wide-open playing field.
But I'm guessing as we add more points, that playing field starts to shrink, right? What happens when we hit 4 points?
Things start to get a little more restrictive. With exactly 4 points in each set, one camera, let's say camera A, can still be placed pretty freely, but the position of camera B gets locked onto a specific curve, known as a conic.
A conic. Remind me what those look like again.
Think of smooth curves like ellipses, parabolas, or hyperbolas. They're all conics, and they're defined by second-degree equations.
All right. Okay, so camera B is no longer free to roam. It's confined to a specific path dictated by that conic. And I bet with 5 points, things get even tighter.
You bet. With 5 points, the position of camera B is uniquely determined by the position of camera A. You pick a spot for camera A, there's only one spot where camera B can be to make those images match.
Wow, so 5 points really nailed down those camera positions. And I remember the paper had this really cool visual method for showing how this works, right? Something called the intersecting conic construction.
Yes.
Can you walk us through that?
Absolutely. The intersecting conic construction is a clever way to visualize how those 5 points dictate camera B's position. So we start by choosing an arbitrary position for camera A. Then we construct 5 specific conics. Each conic passes through 4 of the 5 points in the first set and camera A's position.
Okay, so each conic takes a turn, leaving out one of the 5 points. What happens next?
Now we shift to the second set of points and perform a similar construction, but with a twist. We use something called conic cross ratios from the conics we created for the first set. It's basically a way of matching the geometric properties of those conics between the two sets.
I'm starting to see how those 5 points are creating a really tight connection between the cameras. But where does camera B come in?
Here's the cool part. The 5 new conics we created for the second set will intersect at a single point. And that point is precisely where camera B must be located.
It's amazing how this all comes together. So with 5 points, we go from a conic constraint to a single predetermined spot for camera B. And I feel like there's even more to this 5-point scenario, right? The paper mentioned something called a Cremona transformation.
Yes, Cremona transformations are fascinating in their own right. But I think we've covered a lot of ground already and we're just getting started. Perhaps this would be a good place to pause and pick up the thread in part 2 of our deep dive.
Agreed. We've gone from cameras in Flatland to hidden dimensions, fundamental matrices, and null spaces. There's clearly a lot more to uncover in this mathematical mystery. We'll be back in part 2 to explore what happens when we add even more points to the mix.
Welcome back to our deep dive into the world of Flatland cameras. Before the break, we were exploring how the number of points in our scenes really affects where those cameras can be placed to capture the same image.
It's mind-boggling how those points act like these constraints, guiding those cameras into these very specific positions. We saw how with 4 points, one camera gets locked onto a conic. And then with 5 points, both camera positions are like uniquely determined. But I'm dying to know what happens when we add even more points to the mix. Does it get even more restrictive?
It does indeed. As we add more points, the possibilities for camera placement, they become even more limited. But the math also gets a lot more intriguing, delving into the realms of cubic curves and invariant theory.
Cubic curves and invariant theory. Oh, that sounds intimidating. But you know I love a good mathematical challenge, so lead the way.
Okay, let's start with 6 points. With 6 points in each scene, both camera positions are now constrained to lie on specific cubic curves. These are curves defined by cubic equations, meaning they involve terms up to the third power of the variables.
Okay, so instead of conics, we've now got cubics dictating where our cameras can be. But how do we actually find these cubic curves? The paper mentions something called Joubert invariants.
You're right, Joubert invariants are the key here. They're specific mathematical expressions that remain unchanged or invariant under certain transformations. In our case, those transformations are related to how we change the coordinate systems of our Flatland cameras.
So it's like finding those core properties of the system that stay the same even when we kind of shift our perspective a little bit.
Exactly. Now, these Joubert invariants, they're built from combinations of determinants, those expressions with the square brackets that involve the 6 points and the camera center. And the paper provides the explicit formulas for these invariants.
I remember seeing those formulas. They look a little bit like a mathematical jungle. How do they actually help us find those cubic curves?
They actually give us the equations that define the cubic curves. By setting certain combinations of those Joubert invariants equal to 0, we get the equations that describe the paths those cameras must follow.
It's amazing how these invariants acts like a recipe for drawing those camera constraining curves. So we've got our cubics, but there's more to the story, right? The paper also mentioned exceptional points that lie on those curves.
You have a sharp eye. Those exceptional points are fascinating. They're not part of the original 6 points in each scene, but they kind of emerge from the geometry of the problem. And here's where it gets even more mind-blowing. Those exceptional points for the 6-point case are actually derived from the 5-point Cremona transformation that we talked about earlier.
Wait a minute, so the 5-point case is influencing the 6-point case. That's like a mathematical echo.
Precisely. It really highlights how these different cases are interconnected in surprising ways. So for the 6-point case, we have these cubic curves defined by Joubert invariants, and they're adorned with these special exceptional points. And both camera positions are constrained to lie on these curves.
So it's like each camera's on a track, and those tracks are those cubic curves. But are they completely free to move along those tracks?
Not exactly. Once you've chosen a position for one camera on its cubic curve, the position of the other camera is uniquely determined on its corresponding curve. It's like they're linked by this invisible mathematical thread.
Wow. So even though they're on these curves, there's still a very precise relationship between their positions. It's like a mathematical dance, with one camera leading and the other following.
A perfect analogy. Now, ready to crank it up to 7 points.
Hit me with it. I'm eager to see how those camera constraints evolve.
All right. With 7 points, things take another fascinating turn. Invariant theory still plays a role, but instead of defining specific curves, the invariants now give us sets of conics, those second-degree curves we talked about before.
Back to conics. I thought we graduated to cubic.
We did. But with 7 points, we find that each camera center must lie at the intersection of 3 specific conics. And these conics can be directly calculated from the data points and that fundamental matrix.
So instead of being restricted to a curve, the cameras now have to be at the meeting point of 3 conics. It sounds like those possibilities are shrinking fast.
Exactly. And here's the remarkable part. Those 3 conics, they intersect at precisely 3 points, and those 3 points are the only possible locations for the cameras.
So from infinite freedom with fewer than 4 points, we've gone down to just 3 possible locations with 7 points. It's like those conics are acting as a mathematical GPS guiding us to those camera hideouts.
That's a great way to put it. And once again, there's a deeper connection here. Those 3 intersection points, the camera locations, are actually the base points of a specific quadratic Cremona transformation that relates the 7 points in the 2 scenes.
Cremona transformations, again, they just seem to pop up everywhere in this problem.
They do, and it really emphasizes how interconnected these different mathematical concepts are.
It's like we're unraveling a complex tapestry, and each thread we pull reveals another intricate pattern. What happens when we push it even further and add 8 or more points? Does the game just end?
You're right, that's where the game ends. With 8 or more points, there's absolutely no way to position the cameras to create the same image. The constraints become too tight, the puzzle unsolvable.
Wow, so from infinite freedom to just 3 possibilities and then suddenly no possibilities at all. It's amazing how the number of points completely changes the rules of the game.
It really highlights the power of geometric constraints and how they can kind of dictate possibilities in ways we might not expect. We've seen how cameras, points, and curves, they intertwine in this fascinating dance, all choreographed by the number of points in the scenes.
This has been such a mind-bending journey. We've gone from basic projections to fundamental matrices, explored null spaces, and even delved into invariant theory and Cremona transformations. It's clear that this seemingly simple problem in Flatland has opened a door to some pretty deep mathematical concepts.
Absolutely. And I think what makes this problem so compelling is how it bridges these different areas of mathematics, algebra, geometry, and invariant theory to provide a complete and elegant solution.
It's a reminder that math isn't just a bunch of isolated topics, but this beautifully interwoven tapestry of ideas. Before we wrap up, I'm curious to hear your thoughts on something. This entire deep dive has focused on Flatland, this 2D world. But what happens when we step back into our own 3D reality? Do you think similar principles might apply?
That's a fantastic question. And it's one that researchers are actively exploring. Imagine trying to understand how 2 cameras in our 3D world can capture the same image of different scenes. How would the number of points in those scenes affect camera placement? It's a complex problem, but I suspect there might be some intriguing parallels to our Flatland adventure.
That's definitely a topic for another deep dive. For now, I think we've given our listeners a pretty solid understanding of this fascinating Flatland camera conundrum and all of the intricate mathematics involved.
Yeah.
Any parting thoughts for our audience before we conclude part 2?
I would encourage everyone to just keep that sense of curiosity alive. This problem reminds us that even seemingly simple questions can lead to some really profound mathematical insights. There's always more to discover, more to learn, and more to connect.
Well said. We'll be back in part 3 to wrap up our deep dive. But in the meantime, keep those minds curious. and those mathematical imaginations firing. Welcome back to the Deep Dive. We've been on quite a journey through this world of Flatland, exploring how two cameras can create the same image from different scenes, all thanks to some pretty mind-bending math.
It's been a wild ride.
It has. We've seen how the number of points in those scenes acts like a set of rules, dictating where those cameras can be placed. Fewer points, more freedom for the cameras. More points, they get locked into these increasingly specific positions.
Exactly.
We've explored fundamental matrices, null spaces, conics, cubics. We've even dipped our toes into the world of invariant theory and Cremona transformations. It's been a whirlwind, but I feel like we're starting to piece together the bigger picture.
It is a beautiful illustration of how these different areas of mathematics all come together to solve this seemingly simple problem.
Yeah.
And as we kind of wrap up our deep dive, I think it's worth taking a step back and reflecting on, what we've learned. What are the key takeaways here?
I agree. So for our listener who might have just tuned in, can you give us a quick recap of the key takeaways from our exploration?
Sure. We started by imagining two robots with cameras exploring this 2D world, Flatland. And the question was, could those cameras capture the same image of two different scenes? And if so, where could those cameras be positioned?
And the answer isn't so straightforward. The number of points in those scenes, that plays a crucial role.
Exactly. With fewer than 4 points, the cameras have tons of freedom. They can be practically anywhere, and we can still find positions that produce identical images.
But with 4 points, things start to get interesting. One camera gets constrained to a conic, right? Smooth curve defined by that second-degree equation.
And then with 5 points, both camera positions are uniquely determined. There's only one configuration that will work. We even explored this visually with that intersecting conic construction. It shows how those 5 points create a very precise relationship between the camera positions.
And this 5-point case introduced us to this really cool concept of a Cremona transformation. It basically describes how those camera positions are linked. It's like a mathematical dance with one camera leading and the other following.
Right.
Then we jump to 6 points, where the cameras are constrained to lie on specific cubic curves defined by cubic equations. And these curves, they're determined by those special mathematical expressions, those Joubert invariants, the ones that remain unchanged under certain transformations.
Right.
We even discovered that those cubic curves, they're adorned with these exceptional points that are directly related to the 5-point Cremona transformation. It's like the 5-point case leaves its mark in the 6-point case.
Yeah. And then finally, with 7 points, we found that each camera center must lie at the intersection of 3 conics, those second-degree curves that we talked about earlier. And these conics, they intersect at precisely 3 points. And those 3 points, those are the only possible camera locations.
So with 7 points, the possibilities dwindle down to just 3. And with 8 or more points, there's no solution at all. It's like the constraints just become too tight.
Exactly. It's a remarkable journey. We go from infinite freedom to just a handful of possibilities, and then ultimately to no possibilities.
Yeah.
It highlights how these geometric constraints, how they can shape what's possible in these sometimes unexpected ways.
Definitely. And all of this is happening in Flatland, this 2D world. It makes me wonder about the implications for our own 3D world. If we were to apply these same principles to cameras capturing images in 3 dimensions, what kind of constraints might we encounter?
It's a question researchers are actually looking into.
Right.
How would the number of points in those scenes affect camera placement? It's a complex problem, but I suspect the lessons we've learned in Flatland, those could provide some really valuable insights.
It's definitely a topic for another deep dive. But for now, I think we've given our listener a good grasp of this fascinating problem and the intricate mathematics behind it. Any final thoughts before we wrap up?
I think the takeaway here is just that even seemingly simple questions, those can lead to some really profound mathematical discoveries. This problem's taken us on a journey through projective geometry, linear algebra, invariant theory. It shows how interconnected all these different areas of math really are. It's a testament to the power of mathematics, how it can reveal hidden patterns and connections in the world around us.
Absolutely. It's a reminder to stay curious, keep exploring, and never underestimate the power of a good mathematical challenge. Thanks for joining us on this deep dive into the world of Flatland cameras. And until next time, keep those minds curious. Welcome to another deep dive. Today we're going to be exploring this super interesting problem where geometry and computer vision totally collide.
Yeah.
It's going to make you think differently about how we see, honestly.
Definitely.
Like, picture a world that exists only in 2 dimensions, kind of like Flatland from that classic novel.
Right.
So our challenge today is to figure this out. When can 2 sets of labeled points, like on different planes, be projected onto the same line? So they look identical, basically.
Yeah, it's a fascinating question, and it's actually inspired by a paper called A Computer Vision Problem in Flatland.
Oh, cool.
The authors, there's a few, Samir Agarwal, Aaron Connolly, and Elisa Cornell, Timothy Duff, and Rekha R. Thomas.
Wow.
They use this really neat idea of flatland cameras,
Okay.
which are essentially these rank 2 linear projections from P2 to P1. And they use this idea to simplify the problem.
Okay.
They delve into the conditions that you need to achieve this common image. And get this. The solutions are tied to these amazing geometric shapes, like conics and cubics.
Wow.
And these shapes actually dictate where those cameras can be placed.
That's so cool.
So before we get lost in the beauty of those shapes,
Right.
let's address the fundamental question here.
Yeah.
Is it even possible to create a common image from 2 sets of points that are in different planes?
Yeah, that's a great point. It's like we're laying the foundation
Right.
before we start building our geometric masterpiece.
Exactly.
So is it possible?
Well, the paper's theorem 2 provides a clear answer. It says, 2 sets of points in the plane can be projected to the same image on a line if and only if they are themselves projections of a common set of points in 3D space.
So it boils down to whether we can reconstruct those 2D point sets in 3D space. That's pretty mind-blowing. It connects this abstract geometric problem to something very real.
Absolutely.
3D reconstruction, which is at the heart of computer vision. Think about it. When we see a 2D image, our brains are constantly trying to reconstruct the 3D scene.
Exactly. And this paper provides a framework for understanding those geometric constraints that govern those reconstructions. Now, the question is, how do we determine if such a 3D reconstruction is even possible? This is where the paper takes us on this fascinating journey into the world of the fundamental matrix.
Okay. I've heard of the fundamental matrix in computer vision, but how does it apply to this flatland scenario?
Well, Theorem 4 introduces this concept of a fundamental matrix in this flatland context.
Okay.
And it states that these projections exist only if there's a special fundamental matrix, a 3x3 matrix with a rank of 2. And its relationship to the camera centers, or epipoles, is critical. The epipoles are basically the projections of each camera center onto the other camera's image plane.
So the existence of this fundamental matrix, with its specific properties, tells us whether or not those 2 sets of points can even be projected onto the same line.
Precisely. And if we zoom out a bit and connect this to the broader world of computer vision, we see that this flatland version of the fundamental matrix is directly analogous to the one we use in 3D computer vision.
Oh, interesting.
And Theorem 5 beautifully illustrates this connection, explaining how the fundamental matrix in both 2D and 3D captures this essential relationship between images captured from different viewpoints.
This is where it starts to feel like we're solving a mystery. We have our clues, those sets of points, the potential camera locations, and we're using this tool, the fundamental matrix, to figure out if those points can even create the same image.
And like any good mystery, there are twists and turns.
Oh.
The paper introduces these fascinating mathematical objects called invariants, specifically bracket polynomials. And these invariants help us differentiate between different camera viewpoints because they remain unchanged under specific transformations.
So imagine you're looking at a painting from different angles. The colors might seem to change, but the underlying composition, the relationships between the objects in the painting, that remains the same. So these invariants are like the underlying composition of our problem.
That's a great analogy.
They stay constant, even when the camera perspective changes.
The paper uses these invariants to define a geometric object called the camera center's variety. And this variety represents all possible camera positions that are consistent with our 2-point sets. Lemma 17 and definition 19 describe the dimensions and multi-degrees of this variety. And this gives us vital clues about the number and complexity of solutions that we might find.
It's like we're mapping out the entire territory of possibilities, exploring all the places where those cameras could be hiding.
Exactly.
To create that identical image.
Exactly.
But we're not just interested in whether a solution exists. We want to know how many solutions there are.
Of course.
And how to find them. And luckily, the paper doesn't leave us hanging. It takes us step by step through different scenarios, starting with a case where we only have 4 points in each set,
Right.
denoted as n and 4.
Right.
What happens in this case?
This is where the exploration becomes even more intriguing. Theorem 20 states that with 4 points, we have, surprisingly, a lot of flexibility.
Yeah.
One camera, let's call it A, can be placed almost anywhere. It just needs to avoid landing directly on one of the points.
Okay.
The other camera, B, has to play by a different set of rules.
Huh.
It's restricted to a specific conic section, a curve formed by intercepting a plane and a cone.
So camera A has a lot of freedom,
A lot of freedom, yeah.
while camera B has to follow a specific geometric path.
Yes.
What determines the shape of that path, that conic section?
The conic cross ratio holds the key. It's a geometric tool that relates the positions of those 4 points to the potential locations of camera B. This cross ratio, calculated using the 4 points in camera A, has to match a specific value that's determined by the points in the other set. It's this beautiful interplay between geometry and constraints.
It's amazing how geometry guides our exploration, providing those constraints that lead to the solution.
Absolutely.
But what happens when we add more points to the mix? Does it become more complex?
It certainly does. Adding a 5th point, moving to Ang5, changes the game significantly. Theorem 27 tells us that in this case, while camera A still has some freedom, the position of camera B is entirely determined by the location of A. It's as if they're now dancing together, their movements intertwined.
I love that analogy, a geometric dance.
Yeah.
So how do we find the exact position of camera B once A is chosen?
The paper unveils a truly elegant solution, the intersecting conic construction.
Okay.
We essentially construct 5 conics, each passing through 4 of the 5 points in the set and the chosen location of camera A. The intersection of those 5 conics reveals the unique location of camera B. It's a beautiful example of how geometric constraints can guide us to a precise solution.
Yeah, it's like those 5 conics are converging to pinpoint the exact spot where camera B needs to be to create that identical image. But we can't stop there. What happens when we push further and add even more points? Does it become even more intricate?
Hold on to your hats because things are about to get more complex. With 6 points, denoted as N6, Theorem 34 tells us that both cameras are now restricted to specific cubic curves.
Oh, wow.
These curves are a step up in complexity from conic sections. They're defined by third-degree polynomials. To figure out these curves, we enter the world of Joubert invariants and Cremona hexadral equations, the mathematical tools that help us navigate this more intricate landscape.
Wow. It's like those cameras are now navigating a more complex maze.
Oh.
And those invariants are the map that helps us find our way. So far, we've seen how adding more points adds complexity,
Right.
but also reveals more intricate geometric relationships. What happens when we reach the limit of 7 points?
7 points.
Theorem 36 tells us that with 7 points, we have a maximum of only 3 possible camera pairs.
And these pairs are determined by the intersection of 3 conics for each camera. And get this, the relationship between the camera centers becomes a degree 5 Cremona transformation. It's a special kind of function that maps one plane to another, and it helps us figure out those 3 possible camera locations.
It's remarkable how this seemingly simple problem in Flatland leads us to these powerful concepts in algebraic geometry.
Yeah.
It shows how interconnected math and the visual world truly are. But this journey has just begun. We've only scratched the surface of this fascinating paper. There's so much more to unpack and explore in this deep dive.
Absolutely. Let's unpack this case of 4 points, where one camera has the freedom to roam while the other is bound to a conic.
You're talking about Theorem 20, right? Where we have these 2 sets of 4 points, X and Y, and camera A can be almost anywhere, but camera B is restricted to that conic sub. It's like A is setting the stage, and then B has to find its place in that setting.
Precisely. The proof of Theorem 20 elegantly utilizes invariants and cross ratios. It starts with choosing a specific vector of invariance denoted as G.
Okay.
And for this scenario, the vector G is defined as 13, 24, 14, 23.
Wait, what are those brackets? It looks like some secret code.
Think of them as shorthand for specific arrangements of the points. Each bracket, like 13, represents the determinant, formed by the homogeneous coordinates of the points indicated within the bracket.
Okay.
For example, 13 would be the determinant formed using the coordinates of points 1 and 3. The beauty of these determinants is that they're invariant under projective transformations.
Uh-huh.
So no matter how we move those points around in a way that preserves straight lines,
Right.
those determinants stay the same.
So they capture the essence of the relative positions of those points.
Exactly.
Regardless of how they're projected, it's like a fingerprint that remains unique even when the image changes.
That's a great way to think about it. Now, to have those two sets of points x and y project to the same image on the line, Theorem 16 tells us that the vectors gxa and gyb must be projectively equivalent.
Okay, let's break that down. What are gxa and gyb, and what does it mean for them to be projectively equivalent?
So gxa and gyb are transformations of our initial invariant vector g. We get them by replacing each bracket, like ij, with a new bracket that includes the camera center. For gxa, we use EJA, and for gyb, we use ijb.
Yeah.
The a and b here represent the homogeneous coordinates of our cameras.
Okay.
For instance, the first entry in gxa becomes 13a, 24a.
So we're weaving the camera positions into our invariant expressions, which makes sense because those positions directly influence how the points are projected.
Exactly. Now, projectively equivalent means that the ratios between corresponding entries in these vectors are equal. This leads to a crucial equivalence. P issue 13x by 24x, 14x by 14 by 24 by 14 by 23 yr, G1, Y2 by 3 by 4a, B1, Y2, Y3, Y4, B.
This equation is packed with information.
Yeah.
It's basically saying that to make those point sets project to the same image, the planar cross ratios calculated around camera A using the points in set X must be equal to the planar cross ratios calculated around B using the points in set Y.
You got it. And remember, we have the freedom to choose A however we like. Once we've chosen A, this equation defines a unique conics section.
Okay.
SUBI sub. It's the conic that gracefully passes through all the points in set Y and ensures that those cross ratio equalities hold true. This conic section beautifully constrains the possible locations for camera B.
It's like we've created a geometric lock and key system. Choosing A sets the shape of the lock, and camera B has to find the right spot on that lock for everything to work.
What's truly fascinating is that this intricate relationship between the camera centers and the conic section isn't just some abstract mathematical curiosity. It has direct implications for real-world applications in computer vision. Imagine you're working on calibrating cameras in a 3D environment. Understanding these geometric constraints could significantly enhance the accuracy of determining the relative positions of those cameras.
It's incredible how exploring this seemingly simple problem in Flatland opens up a whole world of insights into more complex, like practical scenarios.
Yeah.
It underscores that sometimes the most effective way to tackle a complex problem is to find its essence in a simplified form, like to uncover those fundamental patterns that hold true,
Right.
even when we scale up the complexity.
And that's precisely what the authors do. The paper systematically explores more complex scenarios by adding more points to our sets,
Right.
revealing a treasure trove of even more fascinating geometric objects and relationships along the way.
This deep dive is already overflowing with mind-blowing concepts,
Yeah.
and I'm eager to see where this journey takes us next. We left off talking about 5 points and the elegant intersecting conic construction. Let's dive into that.
Absolutely. The case of 5 points is where things become remarkably precise.
Okay.
Theorem 27 states that given 2 sets of 5 generic labeled points, x and y, once we arbitrarily choose camera A,
Okay.
the location of camera B is uniquely determined.
This is where that intersecting conic construction comes into play, right?
Yes.
You have to carefully piece together those conics to find the exact spot for B. It feels like solving a geometric puzzle.
Exactly. The proof elegantly hinges on the idea of 4-point cross ratios and the relationship between point configurations in P1 and P2.
Okay.
Remember lemma 28? It states that 2 sets of 5 points in P1, let's call them P and Q, are projectively equivalent, meaning we can transform one into the other using a projective transformation.
Right.
If and only if the 4-point cross ratios of all corresponding 4-point subsets are equal.
So we're essentially comparing the shapes of those point sets in P1.
By looking at how their subsets are arranged. It's similar to comparing constellations by observing the patterns formed by their stars.
That's a fantastic analogy. Now back to our 5 points in P2.
Okay.
We know our sets X and Y can be projected to the same image in P1. Lemma 28 tells us their corresponding 4-point subsets must have the same cross ratio.
Okay. I'm following along. We're leveraging the fact that the projections in P1 have matching cross ratios.
Yes.
To deduce something about the arrangement of the points back in P2.
Precisely. Now for the key step,
Okay.
We select an arbitrary camera, A, in P2,
Uh-huh.
and construct 5 conics, sub S sub sup sub.
Okay.
Each conic plus sub sup sub passes through the 4 points of X, excluding in sup sub and our chosen A. We then meticulously calculate the conic cross ratio of each sub sup sub.
So we've created these 5 conics in the plane of X,
Right.
each associated with a specific 4-point subset, and our chosen camera, A. What's next?
We shift our focus to the plane of Y for each conic cross ratio we calculated in the plane of X.
Right. We construct a corresponding conic,
Okay.
a sup sub in the plane of Y. Each sup sub passes through the 4 points of Y, excluding u sup sub,
Okay.
and critically has the same conic cross ratio as its counterpart sub sup in the plane of X.
It's like we're creating mirror images of those conics, ensuring they have those matching cross ratios. It feels like we're setting up a geometric trap.
And here's where that trap springs shut.
Oh.
Those 5 conics in the plane of Y, the sup subs, are guaranteed to intersect at a single unique point. That point is precisely where camera B needs to be.
That's incredible. It's like those conics are converging, guided by those matching cross ratios.
Right.
To pinpoint the exact spot where camera B creates the same image as camera A, it's a beautiful illustration of how geometric constraints can lead to such precise solutions.
This intersecting conic construction is indeed a highlight of the paper. It beautifully showcases the profound connection between the geometry of point configurations in P1 and P2.
It's an aha moment that makes this deep dive so rewarding. Who would have thought that this abstract concept of cross ratios could be used to solve such a concrete geometric problem?
It speaks to the elegance and power of geometric thinking. And the paper keeps going, exploring cases with 6 and 7 points, revealing even more intricate geometric relationships and demonstrating how algebraic geometry can unravel these mysteries. I'm curious, what are your thoughts as we move into these more complex scenarios?
Yeah, I'm ready. I'm ready to dive into the deep end with those 6 and 7 point cases.
Okay.
We've seen how things get progressively more complex as we add points.
Yeah.
What new geometric wonders await us?
Fasten your seatbelts, because we're about to enter a realm of cubic curves, Joubert invariants, and Cremona transformations.
Sounds intense.
Yeah.
I'm all for it. Let's start with 6 points. We know from Theorem 34 that both cameras are now restricted to specific cubic curves.
Right. With 6 points, our playground changes. We're no longer dealing with conic sections, those elegant curves formed by intersecting a plane and a cone. Instead, both cameras, A and B, are confined to cubic curves, which are defined by third-degree polynomials. Imagine them navigating these winding paths, their possible locations dictated by these intricate curves.
It's a step up in complexity. For sure.
Definitely.
How do we even begin to define these cubic curves? The paper mentioned Joubert invariants and Cremona hexahedral equations.
Yes.
I have to admit those terms sound pretty intimidating.
They might sound intimidating, but they're actually powerful tools that help us unlock the secrets of these cubic curves. Joubert invariants, for example, are special expressions that capture relationships between the 6 points in each set. These invariants are like a signature for the arrangement of the points, helping us distinguish different configurations.
So we're using these invariants, these signatures, to classify different arrangements of the 6 points.
Exactly.
But how do we actually translate those invariants into the equations of the cubic curves that constrain our cameras?
That's where the Cremona hexahedral equations come in. These equations provide a direct link between the Joubert invariants and the coefficients that define our cubic curves. They're the bridge between the abstract world of invariants and the concrete geometric shapes we're trying to determine.
It's incredible how these seemingly abstract mathematical tools, these invariants and equations, have such a tangible impact on the geometry of our problem. They're not just theoretical concepts, they're the keys to unlocking the specific shapes that guide our camera locations.
And the beauty is that this interplay between algebra and geometry becomes even more profound when we move to the case of 7 points. Theorem 36 reveals that with 7 points, we're limited to a maximum of only 3 possible camera pairs. Each of these pairs is determined by the intersection of 3 conics for each camera. It's like a delicate balancing act, where only a handful of configurations can satisfy those stringent geometric constraints.
Only 3 possible camera pairs? That's a dramatic decrease in freedom.
Yes.
Compared to the cases with fewer points. It really highlights how those geometric constraints become like tighter
Right.
as we add more points. Is there anything special about the relationship between these possible camera locations?
There is. The relationship between the camera centers in this case is described by a degree 5 Cremona transformation. Now, this might sound complicated, but imagine it as like a special map that distorts the plane,
Okay.
taking points in one configuration and mapping them to their corresponding locations in another.
Oh,
This specific transformation, the degree 5 Cremona transformation,
okay.
encapsulates the complex geometric dance between those three possible camera pairs.
It's amazing how these transformations, these maps, provide a way to navigate the intricate relationships between those camera locations. We started with this simple idea of projecting points onto a line in Flatland,
Right.
and it's led us to this like fascinating world of cubic curves, invariants, and transformations. It really underscores the power of geometric thinking
Yeah,
and its deep connections to other areas of mathematics.
it really does.
As we wrap up this deep dive into a computer vision problem in Flatland, I'm struck by the sheer elegance and beauty of geometric thinking.
Absolutely.
We've seen how cross ratios, conic sections, cubic curves, and Cremona transformations all play a part in determining whether two sets of points can create the same image. It's a journey that's both intellectually stimulating and visually inspiring.
I completely agree. And beyond the specific results, this paper reminds us that the pursuit of knowledge is a journey of constant exploration and discovery.
Yeah.
There's always more to learn, more connections to make, and more beauty to uncover in the world of mathematics and beyond.
All right, buckle up everyone, because today we're taking a deep dive into projective geometry and computer vision.
Sounds exciting.
It is. We're going to tackle a problem that's elegant, practical, and kind of mind-bending all at the same time.
I'm intrigued already.
So picture this, a robot living in Flatland.
Flatland.
Yep, a 2D world. This robot's trying to understand its surroundings, but get this, it only has one camera.
Okay, I'm following so far. A robot with a camera trying to see in a 2D world.
Exactly. And here's the question. If it takes a picture of two different scenes from different positions, will those images always be different?
You'd think so, right? Different scenes, different images.
You'd think. But it turns out things aren't so straightforward, especially when you're dealing with projections. Sometimes those images can be the same, even if the scenes are different.
Wait, really? That's counterintuitive.
It is. And that's where the paper we're diving into today comes in. It tackles this problem head on.
So what's the paper's main focus?
It asks a very specific question. Given two sets of labeled points in the plane, when can two different cameras in Flatland produce the same image of them? And if they can, where can those cameras be positioned?
That's a great question, and I'm guessing there's some pretty heavy math involved.
You bet. This paper dives deep into the proofs and equations using tools from projective geometry and invariant theory. Perfect for a math enthusiast like you.
Challenge accepted. I'm always up for a good mathematical puzzle.
Awesome. And what's really cool is that this paper bridges the gap between abstract geometry and real-world applications like computer vision.
So we're not just playing around with theoretical concepts, we're actually exploring something with practical implications.
Yeah, exactly. It even connects to some familiar concepts from computer vision, like the fundamental matrix.
Okay, I'm hooked. Let's unpack this mystery. First things first, when can those Flatland cameras capture the same image of different scenes? What does the paper say?
Here's the key condition. You can get the same image from different camera positions if, and only if, those two sets of points in the plane are themselves projections of a common set of points in 3D space.
So it's like we're looking at different shadows of the same object.
That's a perfect analogy. Imagine shining two lights on a 3D object. You get two different shadows, but they both originate from the same object.
Makes sense. So those different scenes in Flatland are like different shadows of some higher dimensional object.
Precisely. And what's even cooler is that this idea isn't limited to just 2D and 3D. It applies to projections between any dimensions.
Wow, so we could have a 4D object projecting two different sets of points in 3D space, and those 3D sets could produce the same image when projected onto a 2D plane.
It's mind-boggling, right? This simple Flatland problem gives us insights into how projections work across dimensions, which could have implications for all sorts of fields.
Definitely. That's the power of abstract thinking. But for now, let's stay grounded in our Flatland scenario. You mentioned a connection to the fundamental matrix. I know it's a key concept in 3D computer vision, but how does it relate to our 2D problem?
It's a fascinating link. In 3D computer vision, the fundamental matrix describes the relationship between two images of the same scene taken from different viewpoints. It captures how points in one image correspond to points in the other image.
So it's like a geometric translator between two images.
Exactly. And what's remarkable is that the same mathematical structure behind the fundamental matrix in 3D also shows up naturally in our 2D flatland problem.
So our flatland scenario is like a simplified model for understanding fundamental principles of 3D vision.
Precisely. The paper also touches on what happens when we add more cameras to the mix, which gets more complex. The idea of a common set of points in a higher dimension still applies, but guaranteeing a consistent 3D reconstruction becomes trickier.
Multiple viewpoints can definitely make things more challenging. But let's stick with our two cameras in flatland for now. We've tackled the when those cameras can capture the same image when the points are projections of a higher dimensional set. Now, how about the where? How do we figure out the camera positions that create those matching images?
In answer to that, the paper turns to invariant theory. Ready to get a little more abstract?
Bring it on. I've got my abstract thinking cap on.
Awesome. Invariant theory helps us describe the possible camera positions based on the relationships between the points being projected.
So even if we transform the points, rotate, scale, shear, some relationships between them stay the same.
You got it. And those invariant relationships hold the key to figuring out where the cameras can be. The paper uses something called SL2, orbits of point sets. It sounds complicated, but it's essentially a way to group different configurations of points based on their invariant properties.
So by comparing these orbits for two different sets of points, we can figure out if they could have been projected from the same higher dimensional set, and if so, where the cameras must have been.
Exactly. And there's this really cool visual theorem that plays a key role here, Kempis theorem. Imagine a polygon with points labeled 1 to n at its corners. Now connect pairs of these points with lines to form a matching.
Okay, I'm picturing it, sort of like connecting dots.
Right. Each matching corresponds to a mathematical expression called a bracket polynomial, which is based on the coordinates of the matched points. Kempis theorem says that these bracket polynomials are all we need to describe the possible arrangements of points and their invariant properties.
So we can use those bracket polynomials to analyze the relationships between the points and figure out if they meet the conditions for creating the same image from different viewpoints.
Precisely. And then comes this really cool concept called the camera centers variety, denoted as CN.
Camera centers variety, what is that exactly?
Yeah. Think of it as a mathematical object that captures all the possible camera positions for a given number of points, n.
So if we have 4 points, C4 represents all the possible positions for 2 cameras that could capture the same image of those 4 points.
You got it. CN lives in this combined space of camera positions, kind of like a map of where they're allowed to be.
And as we change the number of points, this map changes, showing how the constraints on camera placement become more or less strict.
That's it. We're going to explore this CN in more detail, starting with 4 points. What does C4 tell us about camera placement?
Let's find out.
Okay, so we're diving into the world of C4, the camera centers variety for 4 points. What can you tell me about this variety? What does it look like? And what does it tell us about where those cameras can be?
Well, with 4 points, things are surprisingly flexible. The paper shows that one of the cameras can be placed almost anywhere in the plane. It just can't be right on top of one of the 4 points. Lots of freedom to move around.
So camera 1 is basically a free spirit. But what about camera 2? Does it get to roam around freely as well?
Not quite. Once camera 1's position is set, camera 2's position gets a bit more, well, restricted. It's confined to a conic section.
Conic section. So we're talking circles, ellipses, parabolas, maybe a hyperbola here and there, those classic curves we all learned about way back when.
That's right. And the exact type of conic that dictates where camera 2 can be depends on something called the conic cross ratio. It's a value that captures the relative positions of those 4 points on the conic.
So camera 1's position, along with the 4 points themselves, determines this cross ratio. And that cross ratio then defines the specific conic that camera 2 has to stick to.
You got it. The paper even gives a really neat geometric construction to find this conic. Really shows you how this constraint actually works in a visual way. Blends algebra and geometry so nicely.
Okay, I'm starting to see a pattern emerging here. The more points we have, the more restrictions we put on where those cameras can be. 4 points means 1 free camera and 1 camera stuck on a conic. What happens when we add another point to the mix, bump it up to 5? Does that constraint on camera 2 get even tighter?
You're on the right track. With 5 points, things change significantly. One camera still has freedom to move around, but now camera two's position is completely fixed. One specific spot, that's it.
Wow, no more conic freedom for camera 2, it's locked in. So how do we find this one special point? Does the paper give us any clues?
It does. There's this fascinating construction called the intersecting conic construction. Picture this. 5 conics, each defined by 4 of the 5 points. So each conic passes through 4 points, leaving one out.
Okay, 5 conics, each missing 1 point. Got it.
Now here's the kicker. These 5 conics all intercept at the same point. And that point is the position of camera 2.
That's a really cool way to visualize it.
Yeah.
Like they're all pointing to the same spot, revealing camera 2's secret location. But wait, the paper mentions something called Cremona transformations and exceptional points.
Yeah.
What are those and how do they fit into all of this?
Yes. Cremona transformations are these fascinating mathematical objects that can warp and rearrange geometric figures in interesting ways. They're essentially maps that take points in one space and send them to points in another space. And in this case, we're dealing with a specific type of Cremona transformation, a degree 5-1.
So we have these transformations messing with the geometry, but what about those exceptional points?
Well, when you apply a Cremona transformation, some points can behave a little strangely. Think of it like crumpling up a piece of paper. Some points move around, but some stay fixed. Those fixed points are called base points. Now, if you apply the inverse of that transformation, those base points can explode into curves, creating new points that weren't there before. Those new points are the exceptional points.
So the transformation kind of folds and stretches the space, creating new points out of thin air.
That's a good way to think about it. And in our 5-point case, these exceptional points are really important for understanding the overall geometry of the camera placement.
I have a feeling these exceptional points are going to be key players as we explore higher point configurations. Going from 4 to 5 points changed things drastically from a conic of possible camera positions to one fixed point. Plus these new Cremona transformations and exceptional points. It's getting more complex. What happens when we add another point and go up to 6 points?
Things definitely get more interesting. With 6 points, both cameras are now constrained, but this time they're both confined to cubic curves.
Cubic curves. So we're moving beyond those conic sections into even more intricate shapes. What do these curves look like, and how are they determined?
Cubic curves are definitely a step up in complexity from conics. They have more, well, intricate shapes and interesting properties. For our 6-point problem, the position of each camera is limited to a specific cubic curve, and these curves are determined by what are called the Joubert invariants.
Joubert invariants. Now, those sound familiar. Aren't they related to those bracket polynomials we were talking about earlier from Kempe's theorem?
You have a great memory. That's right. Joubert invariants are specific combinations of bracket polynomials that give us even more refined information about the relationships between points. And in the 6-point case, they're essential for figuring out the equations that define those cubic curves for the cameras.
So those bracket polynomials are like building blocks, and we use them to create these higher-level invariants that capture more subtle relationships. And then those invariants give us the equations for those cubic curves. It's a fascinating chain of concepts.
You've got it. And remember those exceptional points from the 5-point case? They make a comeback.
Wow.
The cubic curves pass through not only the original 6 points, but also those exceptional points.
It's like those 5-point exceptional points are haunting the 6-point problem. But it makes sense. Those points are fundamental to the geometry of this whole thing, so of course they're going to keep popping up.
Exactly. The paper even gives us explicit equations for these cubics, which are derived from those Joubert invariants. And it introduces something called the Cremona hexahedral equations, which give us even more information about the possible camera positions. It's a really rich and complex mathematical landscape.
I love how this question about a robot in Flatland has led us to this world of cubic curves, invariants, and geometric constructions. Shows you just how deep and interconnected math can be. Okay, I'm ready for the grand finale. We've gone from complete freedom to conics to cubics. What happens when we add that 7th point? Does the system just explode with complexity, or do things start to settle down?
Well, get ready for another twist. With 7 points, things don't get more complicated. They actually become surprisingly well-defined.
Wait, really? So instead of curves or surfaces, we're talking about a handful of specific points where the cameras can be.
You got it. All that freedom we had in the beginning disappears. And the amazing thing is that we can find those specific points using the tools we've already talked about.
Okay, I'm all ears. How do we pinpoint those camera positions for 7 points?
There are 2 ways to do it, and they both give us the same answer. First, we can intersect those cubic curves we found for the 6-point case.
So those cubics, which started as constraints, actually guide us to the solution for 7 points.
Exactly. The second way might surprise you. We can intersect conics.
Hold on, conics. I thought we'd moved on to cubics. What's going on?
It's a fascinating twist. These conics aren't directly derived from the geometry of the points like they were in the 4-point case. Instead, we get them from a 2-parameter family of fundamental matrices. Remember those matrices that describe the relationship between the two camera views?
Oh, right. Those fundamental matrices that tell us how points in one image correspond to points in the other. So we're using the fundamental matrix to generate these conics.
Exactly. Each fundamental matrix in this family represents a different possible relationship between the camera views. And if we consider all the possible fundamental matrices within this family, we can derive 3 conics that must all intersect at the position of one of the cameras.
And because we know that with 7 points there can only be a finite number of camera positions, those 3 conics must be intersecting at exactly those allowed positions.
You got it. It's a very elegant solution that shows the power of linear algebra and projective geometry to solve this kind of visual problem.
I'm really blown away by how everything comes full circle. We started with simple projections, then got into invariant theory and cubic curves, and now we're back to conics, all connected by those fundamental matrices. It's an incredible symphony of math.
It really is. And there's another interesting thing about those conics in the 7-point case. If the coordinates of the 7 points are rational numbers, those conics have infinitely many rational points.
That sounds pretty technical, but I bet it's important. Why does that matter?
Well, it's really helpful for practical applications. You see, in real-world situations, the measurements and coordinates we deal with can often be expressed as rational numbers. So this property means we can find lots of camera positions with nice rational coordinates that satisfy all the geometric conditions.
So instead of having to mess around with complicated irrational numbers, we can stick with those computationally friendly rational coordinates, which makes things much easier for algorithms and calculations.
Exactly. It's a perfect example of how an abstract mathematical property can have real-world consequences.
You know, as we've been talking, I've been thinking about that connection to the fundamental matrix. Again, it's such a crucial tool in 3D computer vision that it seems like it arises very naturally from our exploration in Flatland. Can you talk a bit more about that connection?
Sure. The fundamental matrix, which we usually denote as F, is a 3x3 matrix that captures the epipolar geometry between 2 views of a 3D scene. It basically tells us how points in one image correspond to lines in the other image. And this correspondence is there because any 3D point, when projected onto 2 different images, will lie on a pair of corresponding epipolar lines.
So the fundamental matrix is like a dictionary, translating between the languages of 2 images.
That's a great way to think about it. It provides that mathematical link between the 2 views, and we can use it to extract 3D information from those 2D images.
And here's the really cool part. This same idea, which is so important for 3D vision, comes up very naturally in our simplified 2D Flatland problem. It's like Flatland is giving us a glimpse into how 3D vision works.
Precisely. The paper does a great job of illustrating this connection by showing how the constraints on camera positions in Flatland, especially for the 7-point case, can be expressed using the fundamental matrix.
So those conics that we got from that 2-parameter family of fundamental matrices are essentially capturing the same geometric relationships that control epipolar geometry in 3D vision.
You got it. It's like those conics are the shadows of the epipolar lines projected onto our Flatland.
I'm really starting to understand why this paper is so important. It's not just about solving a fun geometric puzzle. It's about revealing these deep connections between abstract math and the real-world challenges of computer vision.
That's exactly it. And those connections go beyond just vision. These math tools and concepts are used in robotics, image processing, even artificial intelligence.
Amazing. It's incredible how a simple question about a robot in Flatland can lead to such wide-ranging insights. But let's not forget about those scenarios with multiple cameras, which we touched on earlier. The paper mentioned that things get a bit more tricky when we try to reconstruct 3D scenes from more than 2 views. Can you elaborate on those challenges?
Of course. As we move beyond 2 cameras, those clean geometric relationships we've been exploring start to get a bit messy.
It seems like the real world always throws in some complications to mess with our beautiful mathematical models.
That's often the case. The paper talks about this challenge, explaining that while the idea of a common set of points in a higher dimension still holds for multi-view reconstruction, it becomes harder to guarantee that we can get one consistent 3D interpretation.
It's like trying to put together a 3D puzzle, but now we have even more pieces, and some might be missing or distorted.
Exactly. And the more cameras we add, the more difficult the puzzle becomes. The paper mentions radial cameras, which have specific projection properties, and suggests they could be helpful for reconstruction. But this area is still a hot topic in research, with lots of unanswered questions.
I can see how increasing the number of cameras could lead to more errors and inconsistencies. We'd need some pretty robust algorithms and statistical methods to handle that uncertainty.
You're exactly right. That's where the cutting edge of computer vision research is headed. We need algorithms that can deal with not just geometric constraints, but also things like noise, missing data, and all the other imperfections of the real world.
So we need to add a layer of statistical thinking on top of our geometric foundation.
Precisely. That's why this field is so interdisciplinary. It brings together mathematics, computer science, and engineering to solve real-world problems.
As we wrap up our discussion of this paper, I'm really impressed by how it demonstrates the interconnectedness of different areas of mathematics. We've seen how invariant theory, projective geometry, linear algebra, even a bit of topology all come together to solve this seemingly simple but surprisingly deep visual problem.
I agree. This paper really showcases the unifying power of mathematics, how seemingly different areas can come together to shed light on a single problem. And in the process, we get these profound insights into the very nature of vision.
And it all started with a robot in Flatland. It's amazing how such a simple thought experiment can lead to such deep mathematical insights.
It just goes to show that even in a two-dimensional world, there's a wealth of mathematical beauty and complexity to discover.
Well, we've definitely discovered a lot today. I think I need another break to let all these fascinating ideas sink in.
I agree. It's been quite a journey. Let's take a moment to appreciate the elegance and depth of this problem and then delve into those open questions and possibilities.
Okay. Phew, I think I've recovered from all that. It's amazing how much depth and complexity we uncovered, starting with that simple question about a robot in Flatland. I'm especially intrigued by the connection between those point configurations, the Cremona transformations, and the fundamental matrices. They all seem to fit together like different pieces of a puzzle, revealing different parts of the same underlying truth.
It's a perfect example of how math can help us see the world in new and unexpected ways. We started with a robot in a 2D world and ended up exploring ideas about 3D vision and the fundamentals of perception.
You mentioned earlier that the paper doesn't just provide solutions, it also raises a bunch of new questions and possibilities. We've already touched on the challenges of 3D reconstruction with multiple cameras and those radial cameras. What other open questions or research directions does this paper suggest?
Oh, there are plenty. The paper establishes a strong theoretical framework, but it also acknowledges that there's a lot more to explore. For instance, one area that's ripe for further investigation is the impact of noise and uncertainty on those camera position constraints. Remember, in our idealized Flatland, we assumed we knew the exact locations of those points.
Yeah, perfect world.
Right. But in reality, measurements always have some degree of error.
That makes sense. In the real world, there are sensor limitations, environmental factors, all sorts of things that can introduce noise. So how do we account for that in our geometric models?
That's a great question. We need to develop robust algorithms that can handle those imperfections. One way is to bring statistical methods into our geometric framework. Instead of thinking of points as fixed entities, we can treat them as probability distributions that represent the uncertainty in their locations.
So like adding a layer of fuzziness to our perfectly precise geometric world.
Exactly. Instead of searching for exact solutions, we can look for the most likely solutions given that noisy data. This adds a whole new level of complexity and requires some sophisticated optimization techniques.
I can imagine that finding those optimal solutions in a noisy world gets pretty computationally demanding. That's where powerful computers and clever algorithms come in, right?
Absolutely. Computer vision is constantly pushing the limits of what's computationally possible. And this paper's theoretical insights give us a strong base for developing those robust and efficient algorithms.
I'm also curious about what happens when we don't have perfectly generic point sets, like we've been assuming. What if some of the points lie on a line or a specific curve? Do those special configurations mess up our models, or do they give us interesting new insights?
Those are fantastic questions. The paper focuses on generic point sets for simplicity, but it acknowledges that special configurations can significantly change things. If some points are on a line, for instance, Some constraints might become redundant, giving us more freedom in placing the cameras. But some configurations could introduce new constraints, making it even harder to find valid camera positions.
It seems like those special cases could either simplify things or make them even more challenging, depending on the specific arrangement of points.
Exactly. That's why it's so important to deeply understand the underlying geometry. It helps us identify those special cases and adjust our methods accordingly. We might need to modify our calculations or tweak our Cremona transformations to deal with those unique situations.
Our discussion is making me realize just how much research is out there, just waiting to be done. We could explore different types of noise, different point configurations, even extend this whole framework to higher dimensions. So many possibilities.
You've hit the nail on the head. Every answer leads to more questions, and every discovery opens up new avenues for exploration. This paper isn't the end. It's the beginning of a whole new set of investigations.
This deep dive has been incredible. Who knew a simple question about a robot in Flatland could lead to such profound insights about vision and the power of math? We've explored projective geometry, invariant theory, Cremona transformations, those fascinating fundamental matrices. It's all connected in this amazing dance of points, cameras, and projections.
And we've only just scratched the surface. There's still so much to learn, explore, and discover. This field is always evolving, driven by both theoretical advances and practical applications in robotics, computer vision, and AI.
I'm so grateful for your expertise and for sharing these insights. I feel like I've gained a whole new appreciation for the elegance and depth of this problem and for how powerful math can be in understanding the world.
The pleasure was mine. It's always a joy to discuss these fascinating topics with someone who shares the same passion for the beauty and wonder of mathematics.
To our listeners, we hope you enjoyed this deep dive as much as we did. We covered a lot of ground, but remember, the journey of discovery never really ends. Keep exploring, keep asking questions, and keep pushing the boundaries of what's possible.